Okay. So hello. My name is Andrea Malchiodi. I'm the current director of the Georgi Mathematical Center. So I would like to welcome you to the center and to the workshop on probabilistic methods in dynamics. So I'll be very quick. I'll just say a few words about the center, so which was founded about 20 years ago, with the goal of being opportunity for the mathematical community in Pisa to meet, even though formally is a research laboratory of Scuola Normale Superiore. So the community of mathematicians in Pisa include people from Scuola Normale, the University of Pisa, and also a small group from Scuola Superiore Sant'Anna. So these institutions, especially apart from the Scuola Normale, the University of Pisa, contribute financially and crucially to the activities of the center. So the activities are workshops, intensive research periods, schools, and we also recently started a colloquium series. So we have visiting positions of two types. So one short term to do research in pairs or in groups, and then we have 2 years postdoctoral positions. Basically, that's all I wanted to say. So I would like to thank the organizers for bringing up this very interesting event, and also to thank the staff of the center for their constant and valuable support. Thank you.
Okay, first of all, let me thank the Centro de Giorgi and Andrea for the kind hospitality and the support they give us, and Federica and Monica, because they really helped us a lot, and without their help, we could not organize this conference. So thank you very much. And now there are other sponsors which helped us. So the university, I have the list here, the University of Pisa, the Italian Minister of Research, it still exists. Then the French, the Italian-French, I say in French, Laboratoire Petit de Sciences Mathématiques. Okay, so it's a French-Italian institution which helps people traveling from both countries. Then the UniCredit Bank, through the project Dynamics and Information Research Institute, whose responsible is Stefano Galatolo, who's here. Thank you very much, Stefano, for the help. Okay, then let me thank the scientific committee. It's composed by John Arnson, who is here, and Breen, he should come soon. Sebastian Guzel and Carlangelo Liverani, they are not here, unfortunately. Paolo Varandas, who is here, and Stefano Galatolo again. And the local organizing committee, Stefano Galatolo is here, Claudio Bonanno, Carlo Carminati, Gianluigi Del Mario. Okay, before finishing, let me tell you about a side event, which is an informal celebration, which will take place on Wednesday to celebrate two of our best friends. One is here, the other probably is coming tomorrow. Okay, so I finished. Now I give the talk. Let's go to start the conference with the first talk by Francoise.
Okay, thank you. Can you hear me now? Yes? Okay. So I will speak about, so thank you very much for this invitation. I'm so happy to be here and back to Pisa, back to Normale conference with lots of friends and colleagues. So thank you very much. So my talk is about mixing in infinite measure on the, what is the problem? Okay. Okay, like this. Okay. Is it okay? Okay. So let's go. So I will speak about the ZD periodic Lorentz gas. So I start with the Z2 periodic one. So I'm interested in the flow. So it will send a couple position velocity at time 0 to the couple position velocity at time t. And so this this model describes the dynamics of a point particle. So with moving with a unit speed, so you can imagine that, for example, it is close to the light speed. And in a domain and with elastic reflection, so meaning that the reflected angle is equal to the incident angle. And we are in something which is Z2 periodic. So I draw a picture when it is Z2 periodic, and you have to just to imagine that my obstacles are just the same, but obtained by translation. Okay. Of course, they are not on the picture, but okay. And there is so you take a position, a speed, and this is the dynamic. And at time t, you are here. Okay. And so, what is so this is a billiard in an infinite table. And what is the domain of the billiard? So in dimension 2, it is so we take a finite number of obstacles and their translation by Z2. And we assume that the OI are open, convex, with boundary C3 and with curvature non-zero. And you take their copy by translation. And we also assume that they do not, that there is no intersection of obstacles. Okay. So, so this is a picture in Z2. The picture in Z is the same, except that the domain will be R times the torus. So you imagine it's on a cylinder, on a tube. And in Z, OI plus L, and when I put plus L here, I mean L0. So this obstacle is maybe here. Okay, and if we start here with this speed, with this velocity, then we arrive here. Okay, etc. Okay, so we take R on the torus. You have the usual identification here. So I will not add additional obstacle. I can, but I'm interested in the. I can add one, for example. Let's say a small one here. I'm interested in infinite horizon. So what means infinite horizon? What means infinite horizon? So it means that there exists a line in the interior of the domain. And I'm more interested in fully dimensional infinite horizon, meaning that so when d equal 2, so when d equal 1, it's like well, fully infinite. So okay. So when d equal 2, it means that there exists a line in there exist two lines, two non-parallel lines and when d equal 1, it's just that there exists an infinite line. Sorry, it's not belonging to, it's contained. What I mean by infinite, this is not finite. This is not infinite, okay? This is infinite. Okay, you can have bounded lines in the torus. So, a real line. Okay, and as soon as you have, in fact, one line, one infinite line, so as I was saying, the picture are not perfect. In fact, you have a corridor of lines, of parallel lines like that. So this is a corridor. You have another one here. And in general, but maybe it's not true on this picture. In general, you have also diagonal corridors. So I have an obstacle here. So okay, picture would be wrong, but okay, I'm not sure there is here. Okay, often there are also diagonal corridors. Maybe here not. Oh, here, oh yes, since I have added this one, in fact, here we do not have just one corridor, but two. One here, and another one here. And all this is a corridor. So we say that there exists one, but in fact there exists more than one. So this flow preserves the Lebesgue measures. And so how can we study this flow? No, this does not move. Yes, this moves. Okay. So from a technical point of view, and I will just make a technical parenthesis. Is that it is very common. So let's write what is the domain of the flow? The domain of the flow here. So phi t is defined on M, which is omega times S1. That you can, well, okay. Then you can quotient if you want by the relation identifying incident, so pre-collisional and post-collisional vector if you want. Yes, if you want it to be really defined. Incident angle. So you quotient by the relation, equivalence relation, saying that an incident vector is equal to a incident vector reflected. If you want it to be very well defined. Just because at the collision time, you have two things that occurs, you see. If you arrive here, you have this point on this vector, and you have this. So you identify both. So the technical point is that if you take a point here, you can represent it by so Q0, V, L0, which is in ZD. Q0 is in one of the obstacles we have in the origin. I mean, one of our finite number of obstacles. So it is in the boundary of this obstacle. V is the same. And finally, an S, which is a positive number. And I will draw a picture. Okay. So where can I draw a picture? I can draw it here. We take a point with some speed. So we say that this is the obstacle O1, and this is the obstacle O2, and this is O1 plus 1, 0. So these obstacles, this point position comes from this point position. So the idea is to discretize time by considering the collisional time. So here it's at point Q0. And this is the Q0, which is here. No, sorry. This is Q0 plus 1, 0. The Q0 is here. Q0 is here. So L0 corresponds to the translation of the original obstacle. And S corresponds to the flight, the length of the flight since the previous collision. So this is S. And you have tau, which is this distance. Okay. And so S has to be chosen between 0 and this maximal length. So you can parameterize QV like that. And doing so, here you have Q0V, in fact, which is just lives on the two original obstacles. And in fact, it corresponds to configuration for the Sinai billiard. So it just you just consider the Sinai billiard. You just count everything by Z2. So you can see it as in the torus. And for the Sinai billiard map. And the Sinai billiard map, starting from Q0 with V. So it's not the same exactly. Okay. You arrive here. Okay. The Sinai billiard maps is this maps which send the post-collisional configuration to the next one, but modulo Z2 in the torus. So here you have something which is in finite measure and which preserve a probability measure. This map, so that I will call T bar. So this is, if this is, let's say X, this is Tx, this couple position speed, T bar X, and this map preserves some measure, probability measure, I mean, it's explicit. I do not write the formula. Absolutely continuous with respect to Lebesgue. We know the density, it's explicit. Okay. So the idea is use this representation. Oh, and there is maybe an additional thing. Well, maybe I will say it later. Okay. So in fact, it's a representation as the suspension flow. And okay, so okay, let's call this position Q1 V1. So the idea, it's a suspension flow. So there is an additional identification. Where can I add it? Maybe here. So when we arrive here, so we are at here it is Q1, here it is Q1 plus L1 plus yes, Q1 plus L1. So this L1 here is 1, 1. And this 1, 1 comes from the fact that we started by 1, 0. And then we add some function, which is just the change cell. So, so there is this identification. When you take Q0V, L0, and you arrive at this time QV, which means that you arrive here. So Q0, it's Q0 and not Q. So I correct. It does not, it depends only on Q0, and this is important. You identify this with, okay, so the arriving, starting from here and being at time tau Q0V, it's here. It's the same as starting from Q1 with the reflected vector. So Q1 with the reflected vector, so let's call it V1. And we are in L1, but at time 0. And what is the L1? What is the relation between L1 and L0? With L1 is L0 plus a function which is the change of cell. Okay, so what happens here is that the change of cell is, so here, no, it's not, sorry, here S1 is 2, is 2, 1. We start from the cell 1, 0, and we have a change of cell, which is plus 1, 1. Okay? And if I start from here, it's the same change of cell. So it only depends on the position, on the speed, and so on the position taken modulo Z2. So this depends only on the dynamics in the billiard, in the Sinai billiard. Tau also. So it's a suspension flow, and you have some probability measure preserving map behind, and then you have well, okay. So this is the technical things that is behind, that is a way to study these systems. Now I will give you the theorems. So there are lots of theorems we can be interested in. So I do not speak at all about the finite horizon case. In the finite horizon case, the position at time t satisfies the usual central limit theorem. Here we are in infinite horizon, and we have a surprising central limit theorem, not the usual one. It is at the position at time t. So you take any probability measure at the beginning, which is absolutely continuous with respect to Lebesgue, and you take the original point with respect to this probability measure, the one you want. And you look at the position at time t, which is something random now. You divide by the square root of t log t. And this converges to a Gaussian random variable with an explicit variance. And this explicit variance is given by the corridors that I drew, just by their width and their period. I mean, it just depends on this corridor is determined by this direction, this vector, and with this width. It's very explicit. It's not given by a sum, an infinite sum. And what is the heuristic idea explaining that? Okay, the heuristic idea is that when you start from QV. Okay. Okay, QT divided by the square. Okay, so this. Okay, I redo things. So you have QV, which is represented by Q0V, L0, which is the cell in which you are at time 0, and S. And now you apply phi t, and you arrive to QTVT, and which is represented by some QNT. and some V and T. And T is the number of collisions before time T. After one collision, it was Q1. After NT collision, it is Q and T. And some L and T and some ST. So when you are interested to QT, in fact, at a bounded number, well, you are close you are at a bounded distance of L and T. And let's say L and T minus L0, which maybe is random, but which is fixed once for all at the beginning, and which does not move with T. And what happens here, you see the difference between L1 and L0 is given by kappa. So when you iterate this, after n collision, it is given by a Birkhoff sum. Of Q0V. So you have a Birkhoff sum here. So this is given by a Birkhoff sum and you say, okay, so this is random. Okay, this is random, but what we know is that the number of collisions converges almost everywhere to 1 over the mean, the average of the distance between two collisions. So this, you can say, okay, it's like T times a constant, T divided by the integral of tau, okay. You can do this, there are usual change of time results. But the difficulty is that we have to deal with that. So this has null integral, this change of cell. But when you look with with the probability measure which preserves the Sinai map, then this is larger than some x. The probability that the change of cell is larger than some x behaves as a constant time x minus 2, which means that kappa is non-L2 with respect to the probability measure. And it's what we call weak L2, meaning that it admits moments of any order smaller than 2, but not moments of order 2. And if you have IID random variable which satisfies this, you have a central limit theorem of this form. So this is the heuristic. If these things were IID with this tail probability, you will get this convergence. This is the heuristic. The real proof is much more complicated. So with Dahlia, we wanted to prove a kind of local limit theorem, but mixing local limit theorem in this context. So we take two functions. And we want them to be continuous. I have no notion of time. I have 20 minutes, great, thank you. Compactly supported. And what we want to prove, well, what we wanted to prove, and this is the motivation we had since several years, was a result of this form. So this is kind of natural once you have the central limit theorem to guess. So, okay, let's imagine, for example, F is just the indicator of a box. I write it for continuous and compactly supported, but of course it is about vague convergence. So it's also for function of this form, in fact. Once you have this for continuous and compactly supported, you got it for it works also for indicator function. And a box, the box is just 0, 1 square times S1. So all the position in a box. And this, what does it mean? It means that you are interested in the Lebesgue measure of points that start from B and are back in B at time t. Okay, you have the same result with so the integral then becomes the measure. Lebesgue B, Lebesgue B. Okay. So this seems to be a very easy function, but in fact, it's a very complicated function in our case. Why? This is one big issue. So we take a box like that. We have this, and we put this. Okay, and so this is our function is the indicator function of this, and we have we are in the middle of the Lorentz gas. Okay. So, but when you are here, you see, you have this infinite line. And this, okay, it's not very important because you, of course, you can neglect this. This has 0 probability measure, okay? But then this means that close to that, you have a lot of points that can go arbitrarily far away. And this is something you cannot neglect. And so this is a difficulty that does not appear when you are in finite horizon. That when you are here, in fact, you are in the middle of a trajectory that comes from far away and that goes far away. It's not at a bounded distance. And so maybe I can say a few words about finite. Okay, if you look at collision time, so if you look to the collision map, like I defined the scenario map, you just consider the time of collision and you ask the same question. So this first theorem has been proved by this. Then this, we can say the two theorems have been proved by Sass and Voryu. Well, in fact, they just proved the weaker version of local limit theorem, but they had everything in their paper which gives the general one. And in this case, the first theorem is easy. It is easy to go from finite time to continuous time. I just explained you how. But for the second one, it's absolutely not the same game. It's not direct to go from the results for collision map to the result for the flow, and there are difficulties, even if the finite horizon case, but here there is this additional difficulty. So the proof of this result is in two steps. So the first step is to consider particular observable. So mixing for specific observable, which are very natural when you have in mind the suspension flow. When you have in mind the suspension flow, you have in mind something like that. Here you have the collision, the configuration at collision time. And here you just have the direction of the flow. And when you arrive here, you go down with the identification I wrote there. And so it's very natural to consider compact in this set, but compact in this set absolutely do not coincide with compact within this set. Compact in this set, what does it mean? It means that, so I said the same, I consider the same function, continuous and compactly supported, but except of saying compactly supported in the domain of the billiard, I will say compactly supported in the domain of the suspension flow. And what does it mean? You can also get function compact close to, I mean, it means that you are at a bounded distance. Here, you can also add this function, but okay. Supported on K. And what does it mean to be in a compact here? It means that your past collision is very close. It's at a bounded distance. And you just fly, you just flew a bounded time. Okay, so I write that. So such that, and we can also then consider that, but this is just a consequence. The closest collision time in the future or in the past is at time bounded by C0. So what does it mean? It means that if you have a domain like that, it's fine. Because your past collision time is at a distance smaller than 1. No problem. You can take also a domain like that, because in the future you will arrive, but you cannot take this, a domain like that. A small ball here. So this is the first tape, and I don't think I will say more about this tape, because Dalia will. I will see, maybe I will come back to that, but I think I will not say more. So see Dalia talk. So in fact, it's a very long talk of 2 talks. Okay, and there is a second step, which is go from this natural function for the suspension flow, but which are very specific for the billiard flow. So I call them particular, even if they are very natural when you just think about suspension flow. To general FG with support. So let's say that in some ball times S1, so in a compact. So to do this, we do it via tightness type result. Do I keep that? Okay. So this is the lemma. So, well, it can be stated by taking the limit of R on the lim sup of T. I prefer to write it with quantificator. So for all R, there exists sometimes T0. Starting from this time, the Lebesgue measure of the set of points that are far away from the closest, well, from the collision time. So I will specify what it means. So this is B. So this corresponds to the integral of indicator of BR times indicator of B composed with phi t is smaller than epsilon r, which is times the normalization we want. Donc T minus B over 2. And what is BR? BR is a set of configurations that are in B, so this B, such that you do not touch the boundary, so such that the heating time here is larger than R. And the idea is that when R goes to 0, then you can neglect this. And so then use approximation by this function and say that, okay, the part that remain is, okay. So the conclusion is just you take this. You approximate by function just by doing that. And there is a symmetric thing in the future. So, well, okay. Compose with phi t. And then you have two error terms. So this is a function which behave to this class. Specific function fg belonging to the class C. This belongs to the class C. Okay, you do the usual trick when you approximate things. And this, you know, it converges to something because of step 1. And this, you know, it is neglectable because of lemma. And then you conclude that it works for any function. Five minutes. Okay. Okay, so what is the idea of the proof of this lemma? I call lemma just because it's technical, but it deserves maybe another classification. So first, we have to neglect some bad configurations. So what is the picture? So I draw it in dimension 2. We are in this small box, and we start from here, and we arrive here. And here, it's very long. It's larger than R. And here you do things like that. And then you come back. Okay. This is what you are looking at, this probability. This is larger than R, this we don't know. So this I call it A, this I call it B, and this I call it X. I mean, in the Sinai billiard, and this score is given by T and X. And so what can we say? Okay. So first we neglect byte configuration. So we neglect, we say that we neglect, what are bad configuration? We neglect when A or B is larger than T log T at the power D over 2 times log R. We then neglect, so here, this is the N, which is here. We neglect the fact that N is smaller than T1P. So first, we neglect the fact that N equal -1, which means no collision. So N-1 cannot happen in dimension 2, but it can happen in dimension 1. Because in dimension 1, you can do something like that and be back without collision. And then we have to deal with this. So the fact that this probability, which means that when you sum the three flights, up to the C1t collision, then you are larger than t. So in fact, this is a large deviation. When tau n is the sum of tau composed with t bar k. And we get this estimate smaller than log t over t. So this is enough in dimension 1 because this is a small o of what do we want? We want 1 over the square root of t log t. So this is fine, but it is not smaller than 1 over t log t. So this is fine in dimension 1. And in dimension 2, we have to go further. We have to take in account the fact that we start from B, but are back to B at time t. Okay, so these things are technical. We decompose the flight. We consider some time. We use some decorrelation, etc. Well, it's technical. So it's by the way, we needed a large deviation estimate in the proof of this lemma. And then once we can concentrate then on the good configuration, which are the configurations that satisfy not this. Okay. And so when this is large, when this is big, it means that you are in a corridor. So being in a corridor, that means that, in fact, what can be said? So here we know something on tau n. So in fact, this displacement should be in the direction of a corridor. So I write like this W1, and I write like this W2. These are the direction of the corridors. So we have to sum over but there is only a finite number of corridors. So we can make this sum. And so we sum just from on this n because we have neglect the other. We sum just on this A because we have neglect the other. And we can also assume that B is smaller than A, and we sum for B between smaller also than T log TD over R. And then what do we sum? Okay, I was a bit good because it's important. So what probability are we considering, in fact? We are considering the fact what can be said about the time. So the time tau n corresponds to the time of this flight. So this time is the time t minus the time a, because we are back at time t here. Here it's 0 and t. Here you have time a, here you have time b. So this should be t minus a minus b at an error of size 1. The kappa n, what can be said about the change of cell starting from here and between this and this? So this kappa n, here you have minus a, so it should be aw1 plus bw2 plus a big O of 1. And we also need kappa composed with t minus 1 larger than a, and kappa composed with tn larger than b. This comes from the suspension flow representation. And now, what do? We do a mixing local limit theorem with error, and we get, okay, it behaves as the product of things times something. This thing is controlled as in Dahlia's talk. So it's very nice. And then we have an error constitute of 3 terms. And for these 3 terms, we have to be careful. And at the end, it works well. Maybe I'll just try the second one. But no epsilon, and there is an additional one. Okay. And I guess it's finished. Okay, so this is a proof. Thank you for your attention. Yes. We have some, well, we did not try to have the optimal one. We just try to have one. So it's explicit, yes. Do we have a, this is the second question. What, yes, what can be said about error? But here, it was not really our problem. Our problem was just to have the equivalent. Yes, of course, we have in mind the question of the error, of course. Yes, so we think it's not, well, what do you mean by higher order? Ah, you mean more than one? Ah, yes. This should work. I am confident about that. But higher order mixing, meaning that we want expansion, this is desperate. I mean, expansions. We can have a rate, a big O, but yes, this should work. Yes. Yes, work a bit more. But it should work. Yes.
Thank you very much for having me. It's great to be here again. I'll talk about something which is rather simple, but I like it a lot for aesthetic reasons. It comes from the time when myself, Ian, and Zemmer were working on fast law systems. The topic I'll talk about has nothing to do with fast law systems. It just came from the attempt to understand better the conventional dynamical systems. My result is pretty easy to state. It's a theorem. It's not yet on archive, even though it's essentially done by my collaborators, Christoph Kuhny, Jeroen Lamb, and Florence Merlevedi. It says that if T from M to M is that thing is a Bunimovich stadium. It's a billiard. It's a billiard map. So first return to the boundaries for the flow. Oh, sorry, flower. Yeah, of course. It's yeah. Maybe my result is wrong. So if it's this, or this is not a billiard, it's a Wojtkowski system of two falling balls. You have ground, you have two balls which fall under gravity, collide between themselves, collide with the ground. The energy is conserved. And in both systems, there are some conditions. Like my result is not true for just any system, but there is a reasonable assumptions for which you have a standard chaotic dynamical system. So if that, and if we have an observable V, which is Helder continuous and centered with respect to the SRB measure, and if we define the Berg of sums in the usual way, Sn is the sum of V composed with Tj, then Bergov sums behave like a Brownian motion. There exists a Brownian motion W such that Sn is equal to Wn plus an error term, which would be O of n to 1/3 log n to 4/3 plus epsilon. And this holds almost surely. All right, so it's easy to state. It's not as easy to understand. Technically, this means that you take the process of Bergov sums, you look at it as a distribution on, I don't know, Kadlak paths, and you say that you can redefine it on the same probability space with a true Brownian motion so that the two are almost surely close together. It's not particularly important what it says. It just says that for many purposes, Bergov sums behave like a Brownian motion, something which we already expect in the forms of the central limit theorem. It has corollaries which are easier to understand. Say that, so this is called almost sure invariance principle, or just a strong approximation. Corollaries could be that S and T divided by root n converges weakly to a Brownian motion. This is as a function of T. Or the law of iterated logarithm. This is called the weak invariance principle. Or the law of iterated logarithm, that is Sn divided by root of 2 sigma log n, sigma squared log n, converges to lim sub converges to 1, or the functional version of the Sn. Oh, yeah, that would have been amazing. This is the law of iterated logarithm. There is a functional law of iterated logarithm which looks at all the limit points of Sn when you do the appropriate scaling. And that functional law of iterated logarithm was what Strassen introduced the almost sure invariance principle for. It was hard to prove otherwise, even for processes like sums of coin flips. Strassen was a probabilist. So these things are the almost sure central limit theorem, which I liked a lot, even if I haven't found use for it. It says that if you look at limit of 1 divided by logarithm n, and you sum over k less than n, 1 over k delta measure at sk divided by root k. Then this converges to weakly to a Gaussian measure for almost every initial condition. So you take a point on your billiard, you compute these deltas at sk divided by root k, you weigh them with 1 over k, you divide by log n, because this is approximately the sum of 1 over k's. You get some probability measure. Well, make this exactly 1 divided by sum of 1 over k's. It will be a probability measure. And this probability measure converges to a Gaussian law for almost every additional condition. So it looks like a Brownian motion. That's what it says. This result is new, but it's not really unexpected. say it just wasn't proved before. It just wasn't proved before. Yeah. Okay, but it's a good question. I can say that this rate is also optimal up to epsilon, up to the logarithmic term, sorry. So we might be able to remove the logarithm or replace it with some lower power, but the end part is optimal. So the almost sure invariance principle for these two systems, it hasn't been proven, which is very strange. I don't think that proving it itself would be a major result, actually. But anyway. Well, the short answer is that, let me give you a long answer. Yes, that's, yeah. Slightly longer answer is it probably should start with Bunimovich and Sinai. So I'll abbreviate well-known names. In 81, they showed that if you consider a dispersing billiard with finite horizon, but otherwise like what Francoise was talking about, we have the weak invariance principle. SNT divided by root n converges to the Brownian motion quite long ago. Then the almost sure invariance principle proved by Melbourne and Nickel in 0509 and by Gazelle in 14. It covers almost sure invariance principle for dynamical systems like, say, the logistic map with Colli-Ekman parameters, or the intermittent map in the regime of summable decay of correlations, or the Sinai billiard, or the Henon attractor with suitable parameters. It doesn't include those systems because essentially these two, they can be factored down to one-sided systems. These are hyperbolic systems. These are non-uniformly hyperbolic. These are non-uniformly expanding. And the argument in Melbourne and Nickel of 509 works by reducing non-uniformly hyperbolic to non-uniformly expanding by using Sinai's trick, which works because these systems are hyperbolic. You have time one contraction along stable leaves. And in that case, you don't have time one contraction along stable leaves. For example, if you look at the trajectory for the Bunimovich flower, which goes near tangentially for a long time, then there is no hyperbolicity along that trajectory. Gazelle's method is different, and I think actually it might apply to those systems with some work, but again, it hasn't been done. The main result of Gazelle is formulated for systems with exponential decay of multiple correlations, which you might have for the some return map for these systems. But anyway, it's not written. Then let's talk about those systems. Chernov and Zhang in 05 proved that that the Bunimovich flower is non-uniformly hyperbolic with return time statistics of at most log n cubed divided by n cubed, which basically means that you have a Young tower with such tails, which implies, for example, rates of mixing. And Balint and Gazelle in also 5. Yeah, they did the same for, oh, sorry. Yeah. So Balint, Borberly, and Varga in 12, they did the same for the Wojtkowski system of 2 falling balls. And then slightly back in time, Balint and Gazelle, they proved the central limit theorem for systems which are non-uniform hyperbolic with these rates without relying on exponential contraction log stable leaves. So these results imply the central limit theorem for the systems of interest. And rather more recently, Melbourne and Varandas proved the weak invariance principle for these systems. They had some kind of natural framework in which you can work with Young towers with polynomial tails without assuming hyperbolicity, only on returns to the base of Young tower. And it was enough to get, in particular, the weak invariance principle, and which is the functional version of the CLT, and lots of other statistical properties. Somehow the ASAP was out of reach, but it's very natural to expect that it holds. The ASAP is rather tricky even in probabilistic literature, even for independent random variables. Its brief outlook is like this. In 65, 66, Strassen proved the almost sure events principle for things like sum of coin flips, and then extended it to martingales for one-dimensional observables, R1. His rates were O of n to 1/4 log n 1/2 log n to 1/4. So this is for martingales in R1. And Kiefer showed that you cannot beat this rate if you work with martingales. There is a certain sense in which whatever martingale you have, well, you cannot get to better if you just rely on the martingale properties. Then in 74, 75. Komlos, Meyer, and Tosnadi. They proved ASAP with rates of the type capital O of log n or little o of n to 1 over p for independent and identically distributed random variables still in R1. So if they had exponential tails, they would get this as a rate. If they had polynomial tails, they would get rates of order O to 1 over p. They were very much afraid of the result. They were young and Strassen was a big figure, so they were very much, and this was thought to be the best rate you can get. But apparently their proof checked out. Their result has been extended in a very long push by people like Einmal, Sakhanenko, Chatterjee, or Zaitsev. Some of this is very recent work, like 2010, and it starts back in 1980s. They proved basically the same rates for d-dimensional observables, and they dropped the independent, identically distributed part. So these just had to be independent. Dropping independence is tricky and rather restrictive. So what we know so far is basically the only result which does good rates in the dependent case is Berkes, Liu, and Wu in 2013, which I'll talk about soon, which does rather special stationary processes in R1. And also there are results which do very general mixed processes in Banach valued spaces by, for example, Kuelbs and Philip. This one? Yeah. Sorry. It's a Bernoulli shift, like the doubling map. Just a doubling map, yeah. You can extend it to a Markov chain. So that's the outline, and then in our proof, we use the result by Berkes, Liu, and Wu because it's the only one which gets good rates in the dependent case. The setup of Berkes, Liu, and Wu, to answer John's question, is like this. The process is the sum of xk's, and each xk is a function of a sliding sequence of epsilons epsilon k minus 1, epsilon k plus 1. And epsilon k's are independent and identically distributed. So it's a two-sided Bernoulli shift. And there are some assumptions on f, that f depends weakly on coordinates with large positive or negative index. It's rather complicated to state, but it holds, for example, if f is like Hölder continuous in a separation metric. We cannot apply just that to our common dynamical systems. So we replace the system, the billiard, by using an extension. Extensions look like this. We require some rather specific properties, but not something uncommon. We have T from M to M, which is a Bunimovich flower or Wojtkowski system of two falling balls. And we construct an extension sigma from delta to delta with a semi-conjugacy pi. We require that pi is Lipschitz. We have a measure mu SRB on M, and we construct a measure mu delta whose push forward is mu SRB. So that's what we require from the extension. It preserves some nice probability measure, and it is Lipschitz. Then if we have an observable V, of which we take Bergov sums, then its lift would be V composed with pi in this framework. What we want to notice is that crucially, the process V composed with T to the N, index by N, is equal in distribution to the process V composed with pi, composed with sigma to the N. So no matter what limit laws you're interested on M, you can just, without changing any probabilistic properties, lift it to the top and work there. And of course, when you do an extension, you try to make the system less complicated than the system you started from. So it might be easier. And then, because the extension is Lipschitz, if V is Hölder, then its lift is also Hölder. That's a general framework. It's some kind of morphism between dynamical systems. On its own, it's quite useless. And of course, you try to find some extension which makes your proofs less complicated. The extension which makes possible most of the results I cited in dynamical systems is that of a Young tower. Young tower as a system on delta, it's impossible to explain in a talk, of course, but very simply it can be thought of as a collection of intervals with a dynamical system which takes things up like any kind of Kakutani tower, and points which cannot go up, they return to the base. And this map is, it takes such an interval, maps it on the whole base with bounded distortions. So it's a system like this with a doubling condition, which basically says it's the same as bounded distortion, that the logarithm of T prime composed with T inverse is locally Lipschitz. For all systems I mentioned before, you can construct such a Young tower. You can have this framework of the extension with pi, with the measure on top, the measure on the Young tower with the natural physical measure, which you have here. And this is a universal framework in which you just have lots of results for free. It's still not enough to apply Berkus-Lewin W, Berkus-Lewin Wu. So what we do instead is what we call different names, say Markov shift tower. Markov shift tower is the same as a Young tower, only your derivative is locally constant. That is, you don't have any distortion. In this setup, if you look at your excursions from the base, which is basically which partition element you take to come back to the base, these excursions are psi mixing. That is, they are close to independent, but not quite independent. In the case of Markov shift tower, the excursions are independent. Which means that you can represent your system as a Markov chain, in the proper Markov chain sense. This is a Markov chain in topological sense, but not measure theoretically. On the other hand, billiards they're Bernoulli measure theoretically, but that proof is not topological, not smooth. So even if you know that they're Bernoulli, it's useless for proving central limit theorem. But it turns out that you can combine both Markov and smoothness of the projection into one and get this. And then you can modify the argument of Berkus-Lewin Wu to work with the almost sure invariance principle. So this is basically what we did some time ago. It's myself in 18 and my collaborators in 18 and 20. We constructed the Markov shift tower for dynamical systems like the aforementioned logistic map or the intermittent map. And we proved the almost sure invariance principle with good rates of the type O of log n to 1 plus gamma with almost optimal gamma, or little o of n to 1 over p, depending on the dynamical system. And our new result, which does most of the proof of the first theorem of my talk, is that we have the Markov shift tower for hyperbolic dynamical systems, including the Sinai flower or the Wojtkowski system of falling balls. It also includes, of course, the Sinai billiards. plus a modification of the argument by Berkes-Liu and Wu gives us the almost sure inverse principle with good rates. I should say that for these two, it's O of, so I gave it in the beginning of the talk, but I forgot now. It has been long ago. For the exponential tails, I think it's log n to 1 plus gamma, and gamma is arbitrarily small. For those two, it's again n to 1/3, log n to 4/3 plus epsilon. And there is an argument that this rate is optimal. It comes from that you look at the length of the excursions. Again, you have some probability to have a tangential excursion of length n. During that time, you can construct an observable so that Birkhoff sums just grow monotonically. And you can say that such a thing cannot be approximated by Brownian motion better than something like this with maybe up to the logarithmic correction. Logarithm can be improved. Peter says that he knows how to, Peter Balint says that he knows how to improve the tail bound for these two dynamical systems, but it's not written up from what I know. I should also say that this construction of the Markov-Shift tower is, it does not require something brand new or complicated. People have been there. Say, for me, it was a modification of the coupling argument from Chernov, Dolgopyat, Young, basically stuff which I learned from Chernov's book on billiards. Roland Zweimüller did almost that for non-uniformly expanding dynamical systems. He ended up with, instead of semi-conjugacy like this, he ended up with that delta and M have a common extension, which is a weaker version than this. But what is curious is that he has done all the technical work. He could have added a couple of paragraphs and got this as well. But somehow he didn't notice, and Dolgopyat, Chernov, Young also didn't notice. If they did, then probably the landscape would have been a bit different, because it's easier to work with Bernoulli shifts, than with Gibbs-Markov maps. It simplifies things like a proof of decay of correlations. So if it was realized when it was, at the time when it was obvious, which is like 2000, then probably some results would have been different. But anyway, we are still able to notice this much later and to even get some good results out of it, like the ASAP for dynamical systems, for which very strangely it's not yet known. Yeah, this was one-sided expanding systems. Here it's properly done two-sided shift. The proof of Berkes-Liu and Wu doesn't care if it's one-sided or two-sided. It's very, very nice. And it's very, I'm happy that we finally record that you have the Markov-Shift tower for two-sided systems. Yeah. Exactly. Yeah, it comes from the height of the tower. If it's polynomial, you get this. If it's exponential, stretch exponential, then you get this, depending on how stretched this exponential is. And tail bound for the Markov-Shift tower is the same which you get for the Young tower, in the sense that if they were polynomial, they stay polynomial with the same parameters. If they were exponential, they stay exponential. You don't get a Markov-Shift tower, but this factors down to a non-uniformly expanding map. This factors down nicely, and these two don't. For macro shift theorem, oh, it has something like this with a Bernoulli shift on top, right? I forgot about it, but the projection is not quite Lipschitz. It was a rather special result. Or maybe I'm wrong, it was long ago. Anyway, in the general framework, there was no two-sided Mark shift tower before. I didn't keep track of time. Can I give another talk? Oh, thank you much. I guess that's it. Not me, but there has been some results even by constructing estimating distances between Sn divided by root n and the normal random variable in some metric. There has been things which estimated this type of distances, which used our paper. Also, there is something new by my collaborators, which uses it, but I didn't look at that quite carefully. Oh, let me say that even though we kind of did something nice, this is, as in real life, it only starts the story. The real challenge now is to do the same in RD. We don't know how. Somehow the arguments are essentially, so when the observable is in RD, the arguments are of Perkos and Wu are very much one-dimensional. We also don't know how to get good rates in the all-machine events principle for flows. Flows require induction, and any induction requires time change of order root n, which screws up good approximations. And also, good results in probability theory, besides the almost sure ASAP, prove things like that the expectation of the exponent of lambda supremum of sk minus wk k is smaller than n is bounded by 1 plus some constant times n. So you have very strong metric which measures how close these things are besides the almost sure component. And we have no idea how to prove results like this, even though we know them for the IID random variables, even in RD. Just an observable. The construction of the Markov shift, it has nothing to do with the observable. Yeah. I don't know, maybe nothing new. I have no idea. You can do already quite a lot with Young towers. This thing just simplifies things. And we found one particular case. I didn't look at it. Thanks.
Okay, thank you. Maybe we are already late, but maybe this talk contains a technical part of which many of you are quite experts, so I can go a little bit faster into the proof. So we are going to talk about extreme events theory for stochastic differential equation, and in particular for observables which are sampled in a discrete time. This is a work in progress with Franco Flandoli, Paolo Giudietti, and Sandro Vaienti. I hope that soon we will have a first version of a first preprint about this. And I have to say, it's the first time I speak about this, so probably I will not be very precise. And I'm also not at all expert in stochastic differential equation. So probably maybe you will help me if there is some technical question. And also about the literature, the literature probably is huge, but we don't know very much. So if someone has some suggestion, please tell us, and we will go and see. So what we are going to see is a statement which is an extreme value law for this dynamical system, which is moved by a stochastic differential equation and some observable. And the interest, at least for me, in this work was also to set up a nice function analytic framework on which we could apply the usual that we know transfer operator techniques with quasi-compactness and Salazar-York inequalities, and so on, which applies to these stochastic differential equations. And so that's why I'm going soon to start talking about how we set up the construction and the proof of the main theorem. So let's go to the kind of system we are going to consider. This is a kind of simple version of a stochastic differential equation. Everything we will take for simplicity something not very general, but the equation we are considering is this one, in which we have a deterministic part, a deterministic flow, which is perturbed by a diffusion, which is generated by this term, which is the Brownian motion. And about the assumption that we take on the deterministic part, the assumptions are quite simple. We ask for some regularity. In particular, we ask B to be Lipschitz. And maybe more important assumption, more characteristic assumption for the approach we are going to implement is this dissipativity assumption, which is stated by this formula. But essentially what this assumption says is that maybe I better take another microphone, phase space, and many important technical things that we are going to do are related to the fact that the phase space is not compact, so it's the full RD. And because of this, essentially we ask that the deterministic part of our system, when we go very far from the origin, this is pointing to the origin in some sense. So if you only flow for the deterministic part of the system, eventually you will be brought to some compact. Okay? And the assumption that we take is this one. Of course, this assumption could be relaxed in some way, but we took this form because it contains the most interesting cases of B that we have in mind for the application, which are the cases in which B essentially asymptotically behaves linearly. There is a dominant linear part, and then maybe inside a compact, it can do whatever it wants, but very far from the origin, it must go linearly. Now, we want to consider some extreme events, and we see these events through the values of a certain observable. So what we do is to take a target point somewhere in our space. The observable that we take is very simple, and also this could be generalized, but for simplicity, let's take this. This is the simplest meaningful one. And what the observable is doing is that it goes to infinity when the trajectory approaches the target point. And of course, what happens is that if we start the system with some initial condition, and we read the observable along a trajectory, we expect the value that we take being unbounded, and we want to see the maximum after a certain time. It will be a kind of the extreme event that happened up to a certain time. And another important thing that we do is that we are not looking at the observable in continuous time, but we discretize the time in this way. We choose a certain time step, which can be any positive number, and we take a sequence of time which are multiple of this time step. This is also in the application not very strange, because many important observers, we have in mind application in things like climate science or other models, and there are many observables which are sampled like every day or every hour or things like this. And what we want to characterize is the way in which the maxima of the observable, so once we have chosen the time step, is a discrete time, and we let the time run from 0 to n-1. We take the maximum of the values that we have seen in this time, and we would like to understand asymptotically how this maximum grows with a positive probability. So you would like to find a sequence of thresholds, and if when you overcome the threshold, this will be the extreme event, and to see if we can find a sequence characterizing how these maximum values grows as the time goes on. And more precisely, we are trying to estimate the probability that is in this formula that represents the fact that we are choosing the initial condition at random with respect. I forgot to say that probably it was written here. Yeah, a system like this has a unique invariant probability measure that we will denote by mu, and this measure is also absolutely continuous with respect to the bag with a positive density. And so since here we put mu even here, it means that we are thinking about, okay, the random part of the system range in the Bernoulli, in the Wiener process, and the initial condition will range in the whole space, but distributed with the invariant measure. So we suppose that the system already arrived to the equilibrium before starting, let's say, this experiment. And what we are able to prove is something like this. If we choose the sequence of thresholds in this way, in a way that the ball centered in the target point with this exponential of un multiplied by n 10 to some number tau, then exponentially this probability not only we know that there will be a positive probability, but we can prove that this is e to the minus tau. And so in some sense, we have an exponential distribution for the 18 times in these small balls shrinking to 0. And this is the result that we are going to prove. And the construction that we make to prove this result is based on the classical Keller-Liverani approach to the rare events, which is based on considering the spectrum of the transfer operator associated to the system and considering a perturbed system, which is the original system in which you includes a small hole representing the extreme events. So we will put a small hole in our phase space, and we will associate an open system in which when you fall in the hole, the probability that fall in the hole will disappear. And since there is a way to know how the leading eigenvalues of the transfer operator on some suitable space change when you insert the hole, and there is a way to relate this with to this equation. And so we are trying to do like this approach for this kind of system. So to do this, now we have to define something that works like a transfer operator for this kind of systems, to find some good spaces on which the transfer operator will have good properties, and then apply the big theorem, the big perturbative theorem, and then prove that the big perturbative theorem gives us this formula. This is what I'm going to say. And I think that this part of the construction is useful in general because, you know, once you do all these standard steps, you can prove many other results. So probably is interesting to see. So the definition of the transfer operator and many quantitative estimates that we can make on our system will be based on a general result that characterize how the solution are distributed in the space that we take from the theory of stochastic differential equation. And to state this result that will be in the next slide, first I have to introduce some notation. The reason why I introduced this notation is the following. First, we are defining this theta t, which is the flow associated to the deterministic part of the dynamics. Why I do this? Because what we are going to see in the next slide is a theorem telling essentially the following thing. If I start from a certain initial condition and I want to know after a time t where this condition is sent after when the evolution of the system starts, essentially the theorem says that, okay, you follow the deterministic flow by theta, and then you spread a little bit by a distribution, and you get another distribution. Of course, you don't get a point, you get a probability measure which is distributed in some way, but this is more or less a Gaussian in the sense that it is in between two Gaussians. Okay, so the system works like this. It follows theta and then it spreads a little bit around something that will be estimated by Gaussian functions. So that's why I introduced this notation. So this theta will be the deterministic flow associated to the stochastic differential equation. And then we need some notation for the Gaussian. And this is what we consider. And given this, there is this general theorem, which is quite recent, by the way, but probably this is recent because it's very general, and there are previous results that arrives here, I think maybe from almost 100 years of work. However, this result says the following thing. Let us fix some big time for which when we stop the evolution we want to consider. Then for all the small t smaller than the big time, let xt, big xt, be the solution of the stochastic differential equation starting from the initial condition small t. So xt will be a random variable that change in the time. The theorem tells us that this random variable is distributed with a certain density, which will denote by st, initial condition, and the other variable in which used to see this as a function. And this density, of course, this will be continuous in both variables. And this density is between two Gaussians, which are centered in the place where you are taken by the deterministic flow. So this is what, like we were saying here. This is for any small t smaller than the big T. Why there are two T? Because the constant depend on the big T. And then the constant are uniform for any small t between this constant. In general, the theorem, if I well remember, the stochastic differential equation is like this. Here in front of the Brownian motion, you can have some function, something complicated. But if I will remember, it's additive like this. I don't think there is Brownian motion inside. So you can have something complicated here in front of dw, but the structure is like this, if I will remember. And the situation is also much more general in B, which is in their assumption was Helder, if I will remember. And so to treat with the older case, since you have not uniqueness of the solution, is a bit more complicated, but we don't want to go in these in these complicated details. Once B is Lipschitz, the solution is unique, and the theorem simplifies a little bit. Okay, but this is very useful because it says that these densities are bounded. It says that they are positive everywhere. And we also have some quantitative estimate for the gradients. So everything is also smooth. Now, starting from this, we start to define some operators related to how the system let evolve densities and measures and things like this. First, we start defining what is called in this context the Kolmogorov operator, which is an averaged composition operator, like an anil.ch operator associated to the system. And the operator is defined like this. Suppose you start with a certain, let's say, observable, which will be bounded. The evolution of the observable is nothing but the composition of the observable with the dynamics averaged on all the possible realization of the random part. Okay, this is like the Koopman operator. It is a kind of annealed Koopman operator. But the useful thing is that we know that this X will have a density, so we can also express this in this way. And this gives us a kind of a kernel operator with a smooth kernel. So you start to understand that you can do whatever you want with an operator which is made like this. And so you start proving basic properties of this operator. And then the next step is, okay, now let's us take the dual, and this will be the transfer operator. And so you define, now we define it directly with S. And we define an operator which acts on L1, and which will enjoy this duality with the Koopman operator. And by this simple formula, it's also easy to prove that this operator has the usual properties that we always use in this case, that is a Markov operator and is a weak contraction with respect to the L1 norm. And this, until this, we are always in continuous time. We can choose any time and let the operator evolve in this way. Now we consider the perturbed operator. As we said, the perturbation of the operator we are interested in is putting a hole around the target point, and the hole will be smaller and smaller. So we denote by Bn the small ball that we have seen before, and we define the perturbed Kolmogorov or Koopman operator in this way. Essentially, we kill the observable inside the ball, and the perturbed transfer operator in this way. So essentially, we apply the unperturbed transfer operator, and then we kill the measure that falls inside the hole. Also for these operators, there is a duality formula, and but from now we cannot use this in continuous time. Now we have to fix the small t, because you see, in this operator there is only one hole. So you are thinking that you have fixed your time step, you evolve, then you put the hole, and then the first step is done. Next step, you will do the same, but now you have fixed the small t. Okay. In continuous time, if you want to generalize this to continuous time, that will be more complicated. This is the technical reason why we. Yes, one idea would be like this. You could, but okay. Let us stay in continuous time, because unless the things are complicated, while in this discrete time things are very simple and quite standard at the end. We define the operators. Now we start looking at the spaces on which we want this operator to act. We know that at the end we want that the transfer operator should regularize in some sense when acting on this space, and we have two properties that can provide a regularization. The first one is the noise. The noise is smoothing. So in a local sense, everything gets smooth and regularized. The second one is the dissipativity. Since everything is brought to a compact, a good way, one idea to realize, to exploit this property as a regularization property is to define a norm which put less regularity far from the origin and more regularity near to the origin. So we'll define a weighted norm. So we start with this. Let us consider a weight function, which will be a function which will be always positive and going to infinity at the infinity. And consider, we define this L1 alpha norm, which is essentially L1, but with a weight. So the functions, the densities having finite norm for this norm will be a certain space, which is not hard to prove that this is a Banach space. And I forgot what I was to say. The function for which this norm is finite, of course, they have to go to 0 at infinity, but they have to go to 0 with a certain prescribed speed, which depend on this alpha. The second step is that we want to have a measure for the local regularity. And of course, the noise is smoothing. So at first you can say, oh, for the unperturbed transfer operator, you can take CK, see what you want, but this is not sufficient to deal with the perturbed operator, because the perturbed operator will introduce discontinuities every time you apply the whole. So you need something weaker, weaker than continuity at least. So what works was a kind of bounded variation norm that we define in the usual way that was defined in many words, starting from Keller and Sossol and so on and so on, by the oscillation. So you define the oscillation of a certain density in a certain set like this. This is how the density oscillates in the set. And then you define a kind of BV semi-norm by looking the average of oscillation in smaller and smaller balls that goes around the whole space. But here there is a technical point. Since the whole space is very big and the back measure here is infinite, this will bring some technical complication but you can avoid technical complication by taking the average not with respect to the back, but with respect to something finite. So we define this norm with respect to some probability measure that must have a continuous and positive density. So here the measure decays, and this is the semi-norm that we are going to consider. This is important. It is important that this measure has a positive density everywhere, so you can see locally the jumps everywhere, but it will give less weight to the discontinuities which are far from the origin, because we don't care about them, because they all will be near to the origin, right? Or in a compact set. So at the end, we are led to define a kind of bounded variation weighted space, which we call BV alpha, and with a norm which is the sum of the L1 alpha norm and the oscillation norm. So, and this will be our strong space on which the transfer operator will be quasi-compact. So this space will be like this. They will be densities which are bounded variation and also decaying with a certain speed at infinity. And the control on the variation is the usual one in compact set, while we allow a less strict control when we go to infinity, because we don't care so much what happens around infinity. A first technical step. Now we define what we like as a strong space, what will be the weak space. For the weak space, we take the usual L1 space, and then you like to prove some compact immersion of the strong space into the weak space, and this is true for the spaces that we consider. The proof is by exhausting RD with larger and larger compact. On every compact, you have the usual things. BB is completely immersed in L1, and then you make it larger and larger, and you can prove something like this. And then the second thing is that you want to prove some regularization of the transfer operator on your space. And this is also possible. You can prove that there is a uniform Lazotta-York inequality that holds for both for the perturbed and unperturbed transfer operator, like we expect to need, because we want to apply some perturbative statement for this, the leading eigenvalue of the spectrum of the transfer operator. And again, now I will not go into the details of how to prove this, but the idea is the one that I told you. The dissipativity reduces the L1 alpha norm. The noise smooth the things and takes care of the BV part. And altogether, they produce inequalities like this. Now, I would like to recall the Keller-Liverani perturbative theorem that we are going to use to prove the main theorem. Maybe I will be quite fast because there are many steps. I tried to summarize what we proved to apply the theorem in a certain way that put together the Keller-Liverani result of 2009 together with the older spectral stability statement together with some reformulation that is another paper by Keller alone. And okay, recall that here now we go in an abstract situation. We have a certain operator which acts on some strong and weak space, but recall that this is the BV alpha space and this is the L1 space in our example. And the transfer operator that we consider are like this, putting a hole, and provided we verify a list of things, then we can know how the spectrum is going to change after you put the perturbation. And what you have to verify, essentially you have to verify the comparative bending. Okay, we verified. We have to verify a spectral gap for the unperturbed operator that then you are going to perturb. And this is by the compact immersion and also your inequality. Also, you can verify it. So there will be a leading eigenvector. This will be the density of the unique invariant measure. A leading left eigenvector, which is in our case will be the integral. And then the operator is decomposed in a direct sum of this part, which is the leading part, and another operator which will be less important. And okay, this we know more or less how to verify it. Then there are the properties for the norm that we consider, and this is also verified. This is the uniform Lazotta-York inequality. This is trivial because we use L1, so everything is power bounded. Then we have some assumption that more or less says that the perturbations are not very bad. They are really small perturbation of the unperturbed operator with our spaces and in our framework. And this is the classical assumption on the mixed norm of the two operators, which has to be verified in our case. And then there is another assumption that is more, this is to apply the old Keller-Liverani result, and this is to apply the second one. We have to see that this is going to 0. So this will be the integral of the difference of the unperturbed and perturbed operator applied to function in our strong space. But more or less in our case, these and these are verified in a similar way. And then there is another like small perturbation assumption. I will not go in, but it's more or less the same thing. And then to compute how the leading eigenvalues the leading eigenvalue is perturbed, we have to define a number that here maybe unluckily we call theta, but it's not the same theta as before. This is a number which is called the extremal index, and is the limits of this complicated formula. I'm not going to the detail because, like it happened in many interesting cases, this number is 1, and all this part goes to 0, and so I am with some estimate we can prove that this is 0. And if you computed your theta and you verified all the list of assumptions that we have shown before, all this general theorem put together tells you that the following thing. It tells you that the leading, let's say the perturbed operator Also, the perturbed operator has a simple spectral decomposition as the unperturbed one. In the unperturbed one, here there is 1, because the leading eigenvalue is 1. But in general, this eigenvalue will be smaller than 1 because you are introducing a hole in the system, so you are losing measure. But still, you have a spectral decomposition which is similar. And what you get, which will be important to make the most important computation, is a quantitative estimate on how this leading eigenvalue moves when you introduce the hole. And this is a kind of linear response statement because it tells you the first order of change of the leading eigenvalue. We will see in a short while what this formula becomes in our case. We will estimate precisely. Here, there will be the size of the hole. But okay, so let's go to the proof of the main result. How much time do I have?
10 more minutes.
Okay. Oh, recall the notation. There is a target point. There is a sequence that will be this sequence related to the inverse of the measure of the small balls. The time is the multiple of some h. This is the notation for the ball. This is the notation for the observable. This is the notation for the operators. Okay, we start from what we want to prove. We want to prove this. The first step is to translate this into something that uses the transfer operator. And this will be done with the formula that we proved for how the operator works and how they are composed with each other. So the starting remark is that, okay, if you want your observable to be always smaller than the threshold, it means that your trajectory stays out of the holes for n-1, for n steps, okay? And you want to estimate this probability of the event of being always outside the balls. So this is the same as making the integral of this product of characteristic function of the holes, which are put in the place where they have to be composed with the trajectories of the system. And once you have expressed your probability as an integral, it's not hard to, well, of course, this is an integral on the Brownian motion and on the invariant measure. This part becomes like this. And when you start to see this, it looks like the Kolmogorov operator. And indeed, it's not hard to prove that, you see, we arrive here. This is like the product of many holes, but there is not phi. In this case, phi is the constant observable one. So this integral is equal to this integral. And with some computation, you can prove that this complicated looking integral is nothing but the composition of many Kolmogorov or perturbed Kolmogorov operator applied to one. And then you have to integrate in d mu, but you write d mu as the density of the invariant measure times dx. And then by duality, you get this. What you need to estimate is the iterate by the perturbed transfer operator of the invariant density for n times, and to take the integral. So you know how probability measure you lost after iterating n time your process. And when you see that what you need is to estimate this, of course, the spectrum is very useful because the formula that we have seen before gives you the leading part of what's happening here. And so now we apply the theorem that we have seen before. And okay, we need something more quantitative about this remainder term, which is expressed here. Not only these operators, they all have uniform spectral radius, which is smaller than 1, but they are uniformly small in some sense. But this comes from the classical Keller-Liverani result. And then once you have this, now you rewrite the action of the transfer operator on observables like this, using the spectral decomposition theorem that we have seen before. And then what you wanted to do was to estimate the integral of this. So you put the integral around, and then you discover that, well, I did not say, but when we take eigenvalues and eigenvectors, usually we have to normalize them. We have to choose a normalization. And we can choose a normalization in which these leading eigenvectors are of integral 1. So this part becomes 1. And so we have this formula. And now we put this formula in an exponential form in this way. And now, finally, now we put this in E2 logarithm of this, but we put inside what is this lambda n, the result of the linear response formula for the leading eigenvalue. And if you insert the details of what we have in this application in the formula, in the general formula that we have seen before, you obtain this. So the leading eigenvalue is perturbed in these ways: 1 minus the measure of the whole, with a smaller term that can be neglected. So you put this in the formula, you simplify again because you develop the logarithm at the first order. So you get this. And now we are almost done, because you see this part, which will be the leading part. Now we have to remember how we choose the UN and the balls. They are chosen in a way that this product tends to a fixed number tau. So the leading part will be e to the minus tau. And then you can prove that all the other parts are not relevant. Now there is a final technical thing. You should understand what this becomes when n goes to infinity, but already in the Keller-Liverani result, there is a lemma about this and tells you that this goes to 1. So we are happy, nothing changed. And then at the end, we prove what we said at the beginning, that was the main result. And that's all for what I wanted to say. I have to say that I did not even try to discuss the related literature, but there are some. I don't know about approach of this kind for stochastic differential equation, like using this spectral perturbation theorem. If someone knows, please let us know. But if you think about approaching stochastic differential equation with spectral methods, the literature will be huge, and there is some connection with our environment, but I don't attempt to mention a list of people, because for sure I will forget someone. And about the general related bibliography in the stochastic differential equation community, probably is really very big, but if someone has some suggestion for us and to related paper to look at, please tell us, because I'm not expert at all of this stochastic differential equation. And thank you. Yes.
The real question is what about random times, sampling at random times?
I think this is possible because the constant in the Menozzi-Pesce-Zhang theorem are uniform in T. I mean, if t is, stays in the range, so probably we have to check this random time, but in some fixed range, then everything is uniform. So probably you can treat all the steps in a uniform way and get the same result. But of course, we did not think about this. What we are thinking is to go to the continuous time. But this includes some more technical complication that we are there. Yes, yes. There is a way, we think that. However, yes, there are a variety of things that you can change. This one is an interesting point of view. Since the time is discrete, I don't think it will be much different from what I've said.
Sometimes if you condition the sampling sequence, you get the special paradoxes.
But if you condition what?
The sampling sequence, and then you take the expectation, then you might have some special paradox.
But the time, you mean choosing times that all are related to the, but the time must be independent of what you have seen in the dynamics. Or you want a time that also see the dynamics.
The times are you sample at the finite times. If you take instead of sampling at finite times,
random but unbounded. Okay, this is different because the constants are not uniform. So I don't know in this case what happened. Yeah.
Okay, another question. Yes, what happened to the theta in the end? Because in the final result, like the last slide, there was no theta involved, was just talk.
Which one? Sorry, theta is one. You make the estimation and you discover that this is always one. Yes. Yes, it's a random thing.
I know you can have a neat situation where I think it's not.
Yeah, but
in this case, it turns out it's one.
You have an explicit independence on tau, on how it depends on h.
No, do you think it will change?
Usually it starts from the very beginning. So, but yes, that was
now you fix h, but
It's a dimension, so maybe express it out in terms of h.
if we can go to the continuous case, I think it would be irrelevant. But
no, I'm not sure, but it seems that it doesn't change. But maybe.
for this case, it's no.
Yeah. Yes. Yes.
These results are dependent in some way how you choose the threshold when you define the even.
The threshold must be chosen to satisfy this. Unless you get zero probability, for example, if you choose the threshold is too low, you have zero probability of not overcoming the threshold. And the threshold are chosen indeed in a way that you are in this subtle situation, which you may overcome the threshold with a certain probability, but you may also not overcome the threshold. And the high resolution, let's say, estimate is that you also know what is the probability of doing or not. So this threshold is the limit one in some sense.
Like in the CFT, you have to divide by the variance if you want to get some limited load. It's the same. If you want to get some universal load, you have to take this kind of normalization.
And the distributivity condition on B, and it implies that you have a finite function.
Yes.
But can you just assume that there is a finite measure?
A finite station.
The measure mu is finite.
What I think is that this condition can be relaxed a lot quantitatively. You change, instead of L1 alpha, you change the space of function, making it. No, my idea was like, if you want to deal with a less dissipative system, you start with densities which are already going to zero faster. And then they will be preserved and you get the Lassota-York inequality and so on and so on. For example, if V was only like bounded, probably you have to consider density which decrease exponentially. So with a finite speed, you get an exponential decrease of the regularity in some sense, and you still get the Lassota-York inequality. But if you, it seems to me that in your case, you don't have the quantitative estimate. You only have something like weaker. And then from this, you want to get a quantitative thing. I don't know. So I don't know. I don't, since this is not compact, I don't expect that there is something quantitative that gets out of this. But maybe you can find another compactness argument to make the thing uniform. I don't know, but maybe we can also discuss if you have an idea of how you can do. Thanks.
Okay, can you hear me? I guess it's okay. Great. So thank you very much. I mean, for the opportunity to be back at Pisa. I came here many times, and it's always a pleasure to be in this beautiful city. Yeah. So my talk will be about acute application of exponential mixing and Neville's ergodic theorem to counting problems. So that will be the theme of my talk. But before explaining what I'm trying to count, let me introduce quickly the notion of translation surfaces and saddle connections. So these are the objects that I'm going to count. So translation surfaces are basically surfaces which have an atlas of charts whose changes are given by translations. By the Gauss-Bonnet theorem, that can't be that's not possible on surface of higher genus. So this is why we should allow some singularities, and these are precisely the objects that we're going to look at. But before delving into higher genus translation surface, let me present you a translation surface that everybody knows, which is the flat torus. So which consists of picking a unit square and identifying sides by translations, opposite sides by translations. So this amounts to play Pac-Man on a screen. So if you follow this straight line, then you get out on the other side of the screen and do something like that. And actually, there is no, the general translation surface is basically the same thing that you see for the square, but now you allow more general polygons or collection of polygons. So here in this case, what you get is topologically a surface of genus 1, and then you have a linear flow on this structure. Here you can play the same game. So I took the regular octagon and I identified sides by translations. So if you do this drawing, then you realize that the surface is a genus 2 surface. So you can do it by doing the following trick. You can complete somehow the picture by adding a fake triangles, and then identifying by opposite sides by translation. So if you do that, then the picture that you get is the same torus as before. But now there is a little hole here, which corresponds to this losange here that I drew, right? And now if you identify the opposite sides of these things, then you see that you get an extra handle. So this is a surface of genus 2. Okay, so it's a flat surface. You can just walk, enter here, get out there, but it's a structure living on a genus 2 surface, and there is no contradiction with Gauss-Bonnet, because at this point here, actually this point here is identified with all the other vertices of the octagon. So actually it makes a point which concentrates all the curvature. So the total angle around this point is bigger than 2 pi. And so that is the trick. So you can make everything flat except for one point where all the curvature is concentrated. And why I like this kind of surface is because these surfaces are actually the natural place to study billiards over rational polygons. So if you have a rational polygon, so a polygon whose angles are rational multiples of pi, like here in this L, then you can play the billiard, like Francoise was explaining this morning. And harder than studying this picture here, one thing that you can do is just unfold what people call unfolding the billiard. So you basically, instead of reflecting the trajectory just on the table to keep up going, and then the next reflection is somewhere here, say, and harder than reflecting again, you just keep going, etc. So, and since the angles are rational, just with a finite number of unfolding procedures, you are back to the same pattern. So basically, studying the billiard on a rational polygon or studying the linear flow on a translation surface is the same problem. Right. On the other hand, there is something that's slightly different from what Francoise was talking this morning, is that since there are no convex obstacles here in the middle of these objects, this flow is not hyperbolic. So the techniques that people use to study these things are not hyperbolic or non-uniform hyperbolic results directly on this billiard, but we can get around this technical problem by studying these objects in families. So look at the entire space of transition surfaces and using a renormalization procedure to rather than following a very long trajectory, we apply a renormalization to study a unit size orbit on a deformed surface. And so, yeah, so basically the idea is that there is what people call the moduli space of transition surface, so the whole family of these things. And studying a trajectory on a single transition surface, it's like studying unit trajectories on the family of transition surface. So let me introduce some notation. So I'm going to talk, in this talk, I'm going to use the notation H kappa for the, what we call the stratum of the moduli space of translation surfaces with conical. So I'm going to prescribe the type of singularities that I see by this list kappa, kappa 1, kappa sigma. So these are natural numbers. Okay, so in this case here, this surface belongs to H2. So these numbers here are measuring the excess of 2 pi around this conical singularity. So in this case, you can check that the total angle, I mean, since it is an octagon, the total angle is 6 pi. So 8 minus 2 times pi. And so I put 2 here because 2 is the excess. So this is 2 pi, 2 plus 1. So the excess of 2 pi is 2.
So the excess
Okay.
to pi
This is just a notation. On this space, there is a nice section.
space. There's a nice section.
And sometimes I will use also the notation H1, just to say that it's the same thing. But my translation surface have a unit total area. So I don't want sometimes I want to forget that I can scale my pictures and just pick area 1 objects. But the important thing is that on these spaces there is a nice section of SL2R, because I simply can act with matrices on the plane and the fact that sides which are parallel stay parallel. So this defines an action. And the philosophy of the whole field of what people call today classical dynamics is that understanding these actions, which turns out to be non-uniform hyperbolic, reflects properties of the billiard. Okay, so I'm not going to explain full details, but that's the idea. The idea is that you are trying to understand a system which is parabolic, so Lyapunov exponents are 0, by using a hand normalization process, a kind of inducing, which is hyperbolic. And so you can use the usual tools from probability and dynamics to get information here. Okay, so and for today, what I want to do is the following. I want to understand how trajectories can join these conical singularities. So in other words, what I'm going to do is to look at the problem of joining maybe I should use colors because this is the same. This is one trajectory. This is another one. So I want to understand saddle connections. So which are trajectories? Straight line trajectories joining conical singularities. Why I want to do so? It's because these objects, these saddle connections, they are on the boundaries of these corridors that Francoise was explaining. I mean, every time you see a closed geodesic, since it's a translation surface, you can do parallel deformations of this thing, and they are going to fill what people call a cylinder. Francoise was calling it a corridor. And if you take the maximal cylinder containing this orbit, it's going to stop just when you hit the conical singularity, because here you don't know how to continue because there are 8 possible ways to follow. So corridors are bounded by saddle connections. And so basically, if you want to understand the corridors in these billiards, it's more or less the same as understanding saddle connections. So this is why people in this field are kind of excited about properties of saddle connections. That's a good question. Let's discuss after the talk, yeah. But yeah, there are many ergodicity questions that you can ask related to this corridor, not only for the billiards but also for Z and Z2 extensions. So yeah, but it's a lot of results. So, yeah, let me not mention this thing. But so now I think it's time to state the result that I'm going to try to prove today. So let me introduce some notation, and then I'll give more motivations for why you could care about this problem. So I will fix a parameter A, and then I will introduce the following notation. So omega will be a translation surface. So why this notation for a surface is because I think of a translation surface as the data of a Riemann surface in the holomorphic differential. And this is the usual notation for holomorphic differentials. This is a translation surface, A and R. So this is the counting function. So it should count pairs of saddle connections bounded by R, and and the rectangle generated by the plane has area at most A. Okay. And so in this context, so alpha and beta are saddle connections. And so this integral here is just a fancy way to say that I'm looking at the vector on the plane, or the complex number given by this vector here. Okay, so you could just call them alpha and beta. I'm just following the fancy notation that people like in this area. And then in this context, the result is the following. So it's a theorem. The statement starts with a work of Andrea, Fairchild, and Mazur. And then it was improved by Bunimovich, and this was from last year. And the result is the following. Let mu v be the Mazur-Vich measure of H1 kappa. So what is the Mazur-Vich measure? This is the Lebesgue measure of this space. So the modular space of all translation surface is a nice object. It's a kind of manifold. And here you can see the coordinates. I mean, you can basically use the sides of the polygons and the corresponding vectors to parameterize the formations of the surface. And if you use the Lebesgue measure on vectors, and you take the product, you get this nice measure. And so, talking about a typical translation surface for the Lebesgue measure is really making a typical choice of these sides. And this measure is, of course, a statutory invariant. So it's a very nice measure. So let mu v be this measure, Mazur-Vich. The key thing is that it's not obvious at all, but it's a theorem of Mazur and Vich that this measure is a probability measure. Then, so there is the following. There exists a delta of this measure and a constant so that my counting function, lambda u a r, is essentially quadratic with an error term depending on the surface, which is strictly less than 2. So it's a quadratic. So the counting is quadratic for this function, and this is for mu and v almost every omega. Okay. Little curiosity, why there is my name is not here. I'm talking about the film. There is no. It's because this is Bunimovich is my PhD student, and this is part of his thesis. So I feel the right to talk about his thesis since I'm his advisor. But yeah, so this is not my theorem. But I think it's a nice application of exponential mixing and the ergodic theorem for the flow that I should mention here. That inside this group there is a nice flow, which is acting on this space, which is the diagonal flow, which is what people call the Tashmiller flow, which is non-uniform hyperbolic. And also there is a nice group that I'm going to use at some point, which is the rotation group. Let me give a name R theta, so rotation group. It will be useful to announce Neville's ergodic theorem. But before proving this result, let me give some motivations. So why people care about these kind of results of saddle connections is because saddle connections often tells you information about the structure of this translation surface. So for instance, if omega is what people call a Veitch surface, meaning that the SL2R object is closed, then there exists a knot so that uv less than a knot imply that actually uv is 0, meaning these vectors are parallel. And there is a kind of converse. It's almost a characterization. So special translation surface can be detected from the properties of the saddle connections. So actually you can decide if you are in a special billiard or not just by looking at these corridors. So this is one motivation for this kind of counting problems and trying to understand what happens typically rather than for a special surface. And also there is a result, a prior result, counting rather than pairs of saddle connections, counting saddle connections themselves. Because I was counting, this result is counting pairs, but you can ask what happens about a single saddle connection. And there is a series of results. I should put some names, I mean, by Veitch, well, Andrea for Charlie, Maser, asking Maser, asking Mirzahani Mohammadi, who Neville, who Weiss, and many others. But the idea is that they can show basically that this, if you count simple saddle connections, then this is a constant, which is what people call a Zigovich constant. Plus an error term, which is small. Okay. So the asymptotic is quadratic again. So the idea is that you still get quadratic because the condition of the parameter kind of say that the saddle connections are related to each other. Okay, so let me see. So this is a result that's true for almost every. So this is for mu, almost every omega. And here mu can be any SL2R invariant ergodic probability measure. It does not need to be Maser-Veitch. And also Maser proved the result, which is true for any translation surface, which is the existence of two constants taking care of this counting problem. Okay, so you have for any surface between two quadratic functions, and for almost any, you actually get an exact count. And so, how do people approach this problem? So let me see if I have more things to say. Probably not. No. So how people approach this kind of problem? The idea is another old idea that goes back to the 30s, which was recently reused by Veitch and then many people, which is the Zigovich transform, which actually has a nice history because Veitch was in Marseille. He was jet lagged, but he wanted to see a talk by Margulis on homogeneous dynamics, and he had a problem to solve about translation surface, and he could not follow Margulis except for the definition of the Zigo transform. So he saw that and he found the idea he needed to complete his paper and then went to sleep. And this is what he tells to everybody. He uses it to tell to everybody. But why so the idea is very nice. I mean, the idea is the following. To translation searches, you can associate the set of vectors corresponding to saddle connections. So this is a subset of R2, or if you like, complex numbers. If you give me a continuous function with compact support, I can define the transform, so which is a function now taking values on the modular space, which is just counting how many elements fall into the support of this function. Okay. And so this is the Zigovich transform. So an example, which is not an example because this function is not continuous, but an example, we could take the indicator function of a ball around the origin. And so this means that you are counting the number of short saddle connections, or R, if you want big. Okay. Now comes the magic of this transform, which is the following. So this thing here, this association, this association is a linear function. So if this thing belongs to L1, okay, it's a linear function, which is SL2R invariant, because the measure here, I'm assuming always that it's SL2R invariant. So you can stop here for 2 seconds and realize that a linear function sending continuous compactly supported functions to numbers, it's a measure. So you are saying that this thing here is a measure on R2, which is SL2R invariant, and there are not many. So how many measures there are which are SL2R invariant? And yeah, SL2R invariant. There is the Lebesgue measure and the Dirac at the origin, right? And so this means that integral H1 kappa f hat omega d omega is a constant depending on mu. Integral of f on R2 d Lebesgue plus maybe something else Dirac at 0, 0. I mean Dirac f, so the value of f at the origin. But actually, so you get a nice formula out of nothing, right? I mean, it's kind of crazy because you don't need to, I mean, you don't need to know what space this thing is. It's just that you have this association between points of the space and a nice set of vectors in R2. So you had this kind of correspondence. Out of this correspondence, you built a linear functional. And the existence of this linear functional plus the SL2R invariance gives for free that you have a formula. And in the case of my modular space, I can prove, or asking and Mason prove that this term don't appear. And this is what people call the Zigovich formula. Okay. So basically, the problem of studying this counting problem on modular spaces becomes a problem of understanding functions on R2 up to a constant, which is the Zigovich constant. So this is very nice. Now I mean, I have this function, so the idea is that now I can try to approach the indicator function by this kind of functions, then get error terms, blah, blah. Okay. Yeah. Another thing which is quite astonishing is that if you look at this formula, it says the following, that for all, so just a remark, is that for all epsilon, this formula says the following, that the average of this counting function so this number here is a constant. Maybe if there is a pi here, right? So if you take the indicator function of a ball of radius r, epsilon, then you get this formula for this function out of this example. And so actually you see that, I mean, this term here, which is in principle a function of epsilon, when you average, poof, the dependence on epsilon disappears. So this is a kind of very nice magic formula, the Ziegler-Mitch formula, which was used by Ziegler to understand the massive problem for lattices, so a problem in number theory. So he was studying lattices and how to count short vectors in lattices, etc. And Vitch was using, saw that actually he was not using in any place the fact that he had lattices. It was just this abstract nonsense reasoning. But of course, the work that you need to, I mean, the formula gives you lots of things, but you should pay a price, which is proving that this formula here is L1. And this is what I mean, for the Mesovich measure, it took 30 pages in the Asking-Mazur paper to justify why for this specific case it's L1. It's not an easy problem, but at least it gives you some idea on how you could proceed to attack these counting problems using ergodic theory. For our purposes, we need to understand a little bit more than L1. Actually, the key result, which was proved by Treya for Child Mason and my student Bonafu, was that this transform is not only L1, but it's L2. And so this is why you can pass it to counting. So basically, you can improve the Asking-Mazur result, which is from the 2000s, from L1 to L2. Let me talk a little bit about L2 integrability. Of the Ziegler-Mitch transform. Very quickly. So the idea is that you want to play the same trick. So you want to count pairs. And so to count pairs, now you have a function on R2 times R2. And then you can build a nice function out of pairs. You can integrate H1 kappa, H bar, I mean H2 hats, let's say. There are two variables. Omega, where this thing here is just summing over pairs, UV, H, UV. And you want to know that this thing belongs to L1 or L1 plus to be able to apply the same trick as before. So if you know that this thing is this thing belongs to L1 plus, or since actually this is a sum of pairs and can use Cauchy-Schwarz, it suffices to show that the just one hat belongs to L2. So assuming we can do that, the outcome is that this is again a measure on this space, on this product space, which is SL2R invariant. And so it has some structure, but now it's a little bit more complicated. So the classification of SL2R invariant measures on R4 is not just the origin and the whole space. There are diagonals. So actually, the true formula to get out of this is the following: two heads. You get so basically you have a disintegration of the measure along a kind of diagonal with slope t. Okay. So basically, if you think a little bit about all possible accelerator point measures on this product space, you have just the full measure. So this is the hard measure, or you have extra contribution coming from these kind of generalized diagonals, where there is a relation between U and V. Okay. So the formula is not as nice as this one. That's what I'm saying, but there is a formula anyhow. And this is actually where my CA comes from. So the CA in this statement that I mentioned by Andrea, Fairchild, Mazur, and Bonafou, the constant is coming from this term. I mean, the counting is basically this constant. But now the constant is more mysterious. So actually, computing the CA for different values of A is a hard problem. So we don't know how to solve it right now. But it could be an interesting problem to understand how this disintegration behaves. Okay. Yes, I told you about the exotic Zigovich formula. Yeah, but as I told you, you need to prove a theorem, which is one of the main points, is that actually this thing belongs to L2. And this is for any f and for any mu SL2R invariant. So it does not need to be the Lebesgue measure. Okay? And so in particular, you have this formula for any SL2R invariant measure. But once you understood to this point, you need now to do the painful work that people who do counting problems via ergodic theory know very well, which is treating the error terms that you get from the boundary. Because you have a region, you have a characteristic function, and you want to approach it by continuous function. So there is an error term produced by the geometry of the boundary. And there is where things get complicated in this setting. But we still can rely on Neveu's ergodic theorem to say that basically these things are kind of comparable and we get around. So let me explain that. So what is the idea? The idea is that for technical reasons, there is this trick that people who count things know that if you're counting too many terms, it's better to do a kind of derivative of the counting function, even though this doesn't make sense. But by derivative, I mean the following. You just count objects which have passed half of the size of the threshold. So you're counting annulus to avoid dealing with very different scales. Okay, so you don't want to have different scales, so you kind of bound yourself in an annulus. So it's a kind of derivative. And then you introduce the following set. So let me introduce some notations. So you have this set here. which is the set that we are trying to approach the indicator function. And the key point in these works of these authors, of my student and Andrea Fairchild-Mason, is to realize that this set here that you are trying to approach is not very different from a set which is obtained by flowing the renormalization. So the philosophy is that dA r over 2 is not far, and again I put quote marks, from the following set: GT RA tau, which is actually RA of GT tau. What is the set? So, well, I told you that GT is the diagonal flow. Tau is the trapezoid. So this is a kind of picture that many people here saw, I guess. I mean, it's something like that on the plane. It's a picture that people use a lot for quantum sectors, and I mean, people doing homogeneous dynamics see this thing all the time. So this is a trapezoid, and what is RA? So RA of the trapezoid is what the authors call the fiber trapezoid. So it's the set of vectors so that U belongs to the trapezoid, and V, so V is the kind of the fiber, and the fiber belongs to the set, so RA of U, which is a set of vectors with determinant less than 1, and a condition on the imaginary part. And so let me explain why I'm doing all this preparation work. It's because if you look at these problems here directly, it's quite hard to approach by ergodic theory. The point is that I'm replacing this set, and I forgot to tell that T here is log R. Okay, so again, I'm kind of using renormalization, so I'm kind of accelerating the time by this flow to see something. So I'm going to use ergodic theory of this thing on this set, which is a kind of nice approximation to this. So basically, I'm doing this preliminary treatment of the geometry of the set because I can't control really what's going on. So actually, if you do a picture, which is much better than just looking at these words and formulas and definitions. So the picture is the following. You are taking a vector, which is this U, on a ball of radius R, more or less. And then around this set, you have this slab. Yeah, my drawings are awful, but okay. So this is the direction of the vector U. So the condition of the determinant tells you that your vector lives here, right? Because these are the only vectors that can make determinant less than something. It's just this size plus translations by U. This doesn't change the determinant. So this is the condition of the determinant. So basically the set that you are interested in is the intersection of this thing with the ball. And what I'm saying is that this set is hard to understand because this set does not behave well when you apply GT, because the GT is not preserving the ball. It's exponential T on the vertical, so it's making an ellipsoid, so it's hard. So the idea is that we are replacing this thing by extra conditions on the imaginary parts. And those are nicely behaved by GT, because GT just multiply these things by the same number, exponential T, exponential T. So this condition scales nicely as I move. And so the idea is that I'm replacing this set by this thing. In doing so, I'm introducing little error terms here because there is a difference of area between this set and this thing. So there is a little difference area here, there, and there. I mean, this part here does not belong to dA, but belongs to my set. This part here belongs to dA, but not to my approximation set. So I have to do computations. And if you do them, you realize that NA omega exponential t, so t is log r, NA star, minus pi exponential 2t, so r squared, 1 over 2 pi integral of 0 to 2 pi h a hat d theta. This is small. This is little o of exponential 2t for mu. And now it's Mizorovich really to get this kind of approximation. Almost every omega. I mean, I think it should be for NSL2R, but currently my student can only do it for Mizorovich because the proof is already complicated. You need to use some complexifications come from algebraic geometry of the modular spaces. Anyway, this is the statement that you get where h alpha is the indicator function of RA of the trapezoid. And now you are happy. Why? Because this is exactly the kind of object, this kind of average, is exactly what Neville can treat. So as promised, we got to ergodic theory. So now you're happy because you did all this message with the geometry. So I'm sorry for the long geometric part, but now we got into business. So now we have this. And why this is, I mean, when people who like ergodic theory see this, they are extremely happy. It's because Neville tells you the following. So Neville's ergodic theorem. And actually, I mean, it's not only using Neville, but to get the error term, because here I'm just saying little o. But in the statement of the main result, I did that there is an error term. So actually, you need to effectivize this thing, and this is what my student did based on the work of Neville and Weiss. Okay, but you need but let's pretend that you don't care about error term right now. So we're not using the full power of the exponential mixing property of this flow, which is known by the work of, I mean, this flow here is very nice. So GT mu MV is exponentially mixing. This is work of Avila Guezel Yokos and Avila Guezel. And so you can think that, I mean, this kind of ergodic information we can use to get nice treatment of these integrals. Here, it's not quite only GT, there is this kind of circle thing. So actually the situation in Neville's result is more like you are in the hyperbolic plane and you are trying to understand the equidistribution of large circles. So you rotate on the, so r theta serves to rotate on the hyperbolic plane, and GT is just making the circle bigger and bigger. And then you are doing the quotient. So going to the surface, these circles become equidistributed somehow. So this is what he's saying. The statement is the following. So Neville tells you that 1 over 2 pi integral from 0 to 2 pi of any function here, actually, GTR theta omega dt. These things converge to the average for a mu almost every omega. Okay. Yeah, so actually he says that. So we are going to use this with phi, which is our h hat. Again, provided this thing belongs to L1 plus. And why I'm insisting on this is because it's the same problem again. I mean, what you get in the ergodic theorems is usually nicer results of the correlation when the observables are smooth enough. Say the observables are C infinity, or what people call K finite, so has lots of derivatives in the direction of the circle. But then you want to decrease the regularity to be able to apply to concrete counting problems where the functions are other indicators. And if you want to do that, so to justify the passage from very smooth to to indicator, I mean, you really need this L1 plus. Yeah, so to get this the true statement, what you need is really an error term here. But this can be done for the Mazorovich measure. So actually, Neville's ergodic theorem works like that for any SL2R invariant measure. So actually, it has nothing to do with this space. It's for any SL2R action on a nice space. But to get the effective version, you need to do calculations, and this is only right now only know for this space and for Mazorovich. And yeah, so I think I'll stop here, even though I have, yeah, I think I'll stop here. So thank you very much.
Questions? So what is the approach of a train phase?
Yeah, basically what they did is the following. Thank you. What they did is they didn't have theorem A. Actually, theorem A was known before for Mazorovich, and this was prior work by Andrea, a former student of Mazur, Jung, and Mazur himself. This is from 2017, maybe, for the Mazorovich measure. And so what my student did was extending that for any SL2R invariant measure, taking advantage of new technology that occurred since then, which is the basically the improvements over the Eskin-Mizrahi work. Yeah. But yeah, so this is a crucial ingredient somehow. If you want to rely on this kind of technique of counting by using this geodesic flow there, you need to know this information to be able to apply Neveu. So the first thing that you should do is establish this thing. Of course, there are more things to be done once you get to this point, which is this theorem B. And unfortunately, this only works right now for the Mazorovich measure.
What are there? Question.
This is a good question. So the error terms, to be honest, there are many conjectures. So basically, let me tell you, this is being recorded, right? So no. I can no. There is no problem. I think we can tell the secrets of this field. So basically, what happens is the following: on this space, there are many SL2R invariant measures. There is a countable collection of SL2R invariant measures. Each of them has a spectral, what people call a spectral gap. So the rate of mixing is really exponential, so away from zero. But what people don't know, and it would be nice to know, is if this spectral gap is uniform for all measures in a given stratum. And if you had that, probably the error term would be uniform for all measures in a given. So if you give me kappa, there will be some number associated to kappa, so that the error term is uniform, is away from 2 by that amount. But this is not known. I mean, since the publication of this paper, the question is kind of buried there, and there is no there is no answer. Actually, there is a conjecture by Yokos, which is kind of provocative in the sense that it's the extension of Selberg's conjecture. So Yokos was claiming that for the measure of each measure, the spectral gap should be maximal, which is known only for the modular curve. And so in particular, the error term should be about 1. Next term is really R. Is R squared plus R. But this is all speculation right now.
More questions. Let's again. So the next speaker is Yuri Lima. He'll speak about symbolic dynamics for large classes of non-uniformly hyperbolic free flows.
Okay, so I would like to thank the organizers, both the local ones and the scientific community, for this such a nice conference in such a nice place. And Ian, happy birthday. So I will talk today about symbolic dynamics, and it's actually a result that is not yet on the archive, but I have the preprint. If someone gets interested, I could send to you in a few weeks, as soon as I finish the introduction. So this is a joint work Jeroen Lamb and Sylvain Crovizier. And I will start with an initial setup, which is actually a setup of diffeomorphisms. So consider a two-dimensional diffeomorphisms, let's say infinity. M, you can assume it to be closed, so it's compact without boundary, and assume it has positive topological entropy. So what do we know as soon as we have positive topological entropy? Well, we know that we have many horseshoes by Katox's theorem, and actually, because of the variational principle, F has measures with measures mu and ergodic measures actually. With positive metric entropy. And also because of that, let's say that this metric entropy is bigger than chi, or actually by Whewell's inequality. You know that this implies to you, Whewell's inequality tells that the metric entropy is less than or equal to the sum of the positive Lyapunov exponents. So we are in dimension 2. This tells us, in particular, that the sum of positive Lyapunov exponents is bigger than chi. So you have at least one positive Lyapunov exponent. But you can do the same thing applying the Whewell inequality to the inverse of F. So you know also that the minus the sum of the negative Lyapunov exponents is bigger than chi. So this tells you that you have at least one negative Lyapunov exponent. So the conclusion is that actually you have one positive Lyapunov exponent and one negative Lyapunov exponent. The positive one is bigger than chi, the negative one is smaller than minus chi. So there are actually two Lyapunov exponents, which are both bigger, or let me put like this, outside the interval minus chi chi. Okay? So I'm calling a measure satisfying this and a chi hyperbolic measure. So mu is chi hyperbolic. Because its Lyapunov exponent is outside of this interval minus chi chi. And well, in this context, we have now 10 or 15-year-old theorem of Sarig, which tells you that in these conditions, for every chi bigger than 0, you can find a set like this, which I'm going to call a non-uniformly hyperbolic set with a sharp here on top, a subset of the manifold in which you can construct a countable Markov partition. So this set has a countable Markov partition. And what is nice about this set is that this set supports all chi hyperbolic measures. So whenever mu is a chi hyperbolic measure, it gives you full weight to this set. So this set contains, in some sense, all the points that have some sort of hyperbolicity, at least chi. Countable Markov partition such that mu of n u h sharp is equal to 1 for every mu chi hyperbolic. Okay? So this set, it contains Lyapunov regular points. So for those who are used to passing period, this means that you have, if you have a point which has a spectrum outside of minus chi chi, and when you look at the passing parameters of the sizes of the charts, these parameters don't decrease to 0 exponentially fast, well, these points are going to belong, essentially are going to belong to here. So in particular, it also contains all periodic points which have Lyapunov exponents bigger than chi in absolute value. So it's a rather big set. It actually contains points which are not necessarily Lyapunov regular. So this is what's nice. I mean, there is a kind of list of conditions in which if the point satisfies these conditions, the point belongs to this. And this includes Lyapunov regular points, but it also has some Lyapunov irregular points. Okay. So let me mention actually two consequences of this result. One is actually not included, but it's a follow-up of this paper of Sarig, which is about equilibrium states. So if you have a mu equilibrium state of a function which is holder, and if mu, let's say that it is ergodic, and if this guy has positive metric entropy, then Sarig proved that this system F mu is actually a Bernoulli system, or a Bernoulli times a rotation. I'm not going to write Bernoulli times a rotation, I'll just put Bernoulli into quotes here. Okay? So this is due to Sarig. It was proved more or less at the same time that he proved this theorem. And the idea is that having a countable Markov partition allows you actually to lift measures to a symbolic space, to a countable topological Markov shift. And in the symbolic space, you can apply the ideas of transfer operators and so on to prove that actually equilibrium states coming from Holder potentials, they behave nicely, they satisfy the Bernoulli property, and so the lift of this measure in the symbolic space is Bernoulli. And as we know, projections of Bernoulli are also Bernoulli, so this is the conclusion, the overall conclusion of Sarig. So the idea here is that the existence of countable Markov partition allows you to find an extension of your geometrical model in which you can lift measures, and whenever you can lift measures, you can analyze them in the symbolic model, so it's easier to understand them, and then you project back these properties of the symbolic model to the geometrical model. Okay? Okay, so this is the first consequence. The second consequence, this is heavy, is more recent, is about homoclinic classes of measures. So this is due to Bouzy, Crovizier, and Sarig. So we can define what it means for two measures being homoclinically related. And what that means is that two measures, let's say mu and nu, are homoclinically related to hyperbolic measures, are homoclinically related if you can find a set of two measures for mu, another set of full measure for nu, such that for every point x in A and every point y in B, the stable manifold of X intersects transversely the unstable manifold of Y, and similarly, the unstable manifold of X intersects transversely the stable manifold of Y. So this, when this happens, you say that mu and nu are homoclinically related. So there exists A, this, such that X in A and Y in B implies that the stable manifold of X has a transverse intersection with the unstable manifold of Y, and the unstable manifold of X as well with the stable manifold of Y. Okay? So why is this interesting? Because actually the result of Saric doesn't say anything about, so I can actually put here, so in particular, you can lift, as I was saying, the diffeomorphism to a symbolic space in a way that you have a commuting diagram here. So this is the kind of blueprint of the proof of this. You consider the measure here, lift here, analyze it here, and then project it back. So in the theorem of Saric, nothing is known about irreducibility properties of the topological Markov shift here. And what these guys proved recently is that if you restrict yourself to the set of chi-hyperbolic measures in a same homoclinic class, then you can lift all of them to a same irreducible topological Markov shift. So this is the kind of geometrical notion of irreducibility that allows you to find a single irreducible component of that sigma in which you can lift all of these measures to the same irreducible component above. So the theorem that they proved
Yuri, when you put that symbol, you mean transversal homoclinic point or can be a tangent?
Sorry?
I mean transversal homoclinic point?
Yes, exactly, transversal. Yeah. So let me write the homoclinic class of mu to be like this. So it's all the chi-hyperbolic homoclinically related to mu. So what they prove is that there exists an irreducible topological Markov shift that lifts all measures of a single homoclinic class. Okay? Okay. So this is the initial context that I wanted to mention, and now I'm going to the context of the talk itself, which is of three-dimensional flows. So you have a three-dimensional manifold here, and you have a flow. Let us assume it's infinity for simplicity. I mean, the results, they work under a much lower regularity, which is like C1 plus beta, but let's not forget about that. And we assume that this phi has positive speed, so has no fixed points. And let's assume also that it has positive topological entropy. So because the flow always has a Lyapunov exponent, which is 0 in its direction, in the direction of the vector field that generates it, this means that also you have measures which are chi-hyperbolic. So measures which have positive Lyapunov exponent away from some chi, negative Lyapunov exponent away from some minus chi. So this is somewhat similar to this context of chi hyperbolicity here. Okay, let me give an example of these things. So for instance, if you consider a surface of non-positive curvature, and you assume that, for instance, it's different from the two torus, then the geodesic flow, which lives in a three-dimensional manifold, satisfies this property. It has unit speed, so it has no fixed points. And by a formula from passing from the 70s, it also has positive topological entropy. Okay? So actually talking about this kind of surfaces, and because it's Ian's birthday conference, I think I should also mention that for these kinds of surfaces, or for a subclass of a class of examples of these surfaces, we have a work in which we calculate that you have polynomial decay of correlations with respect to the Lebesgue measure. So let me put here the theorem. So about this, if you consider the following class of surfaces, so you give me an R, which is greater than or equal to 4, and then you consider a function psi of S, which is 1 plus modulus of S to the power R. And if you consider the revolution of the graph of this function with respect to the x-axis, then you get a kind of a neck, or a piece of, or an annulus, in which by simple formulas you can prove that actually the curvature here is negative everywhere except at this closed curve here, which is actually a geodesic inside this surface. So you can glue this neck with negative curvature, and then you get a surface like this, which has non-positive curvature, but it's actually much nicer because you know exactly how the non-positive curvature is occurring, and you know exactly what is the kind of geometry that you have near this closed geodesic here. So the result that we have in this regard here, collaboration with Matheus and Ian, is that calling this number here to be A. So you have an exponent, polynomial decay of correlation. Put F and G. With respect to no, this is fine. Log t to the a. So we found that these kinds of examples, they satisfy a polynomial decay of correlation, and the rate of decay is basically of the order t to the a, where a is this exponent here, which I don't remember, is between 1 and 3. It's a decreasing family. Huh? Sorry? Oh, yeah. Sorry. This is with respect to Lebesgue. This is with respect to Lebesgue. Okay? Okay, so now I will go back to the symbolic dynamics again. Well, this is in fact... Sorry? You can give the... Yes, exactly. If you do the exercise of repeatability, then you can get rid of the log here. Yes. Okay.
Excuse me. A is t at the power A or with another power?
Sorry, this is t to the power a. Yeah. Where a is this number.
So the integral there is divided by t.
This one?
Yeah.
No,
it's an average, or it's not.
It's an average, but you're flowing by t. It's the correlation.
So there's t too many times. There's t on the left-hand side. You're integrating. Oh, you're not integrating with it. Okay, good.
The space. Now we forget the zero here. Yeah. Okay, so coming back to the context of that context there, what can we say about symbolic dynamics? Actually, there is a result which is, I think, almost 10 years old by myself and Farid, which we do the following. Give me a chi-hyperbolic measure. So if you give me a chi-hyperbolic measure, I can find a countable Markov partition. R that has full measure for u. And saying that this is a countable Markov partition means the following. Means that you can represent your flow as a suspension flow over a countable topological Markov shift. So the case of diffeomorphism was just the countable topological Markov shift. The case of flow, you get a suspension over such objects in a way also that the diagram commutes as it commuted. I erased it, but it's a geometrical structure that actually allows you to construct a symbolic representation of your flow. Okay? And I put here fix. So there is a difference between this result and the original result of Sarig in the sense that Sarig's result is able to construct a single Markov partition, countable one, for all the measures which are chi-hyperbolic. And this class of measure is actually usually non-countable, uncountable. Here we were only able to construct for a single chi-hyperbolic measure a countable Markov partition. Actually, the same methods actually allows us to do the same thing for a countable family of measures. So if you give me a countable family of chi-hyperbolic measures, I can come up with a single countable Markov partition that gives full weight to all of them. But if you ask me to do the same thing for an uncountable family of them, then our method doesn't work. So in particular, we are not able to get such a theorem like in Buzzi-Crovisier-Sarig, because the homoclinic class of measures is usually uncountable. Okay? And why is that so? So what is the idea of the proof? Well, we follow what clever people did, and the way that Poincaré analyzed proofs was by means of sections. So we build a section, global section made of the union of many disks, which are almost transversal to the flow direction. And instead of working with the flow, we work with the Poincaré return map to the section. So lambda section, it induces a Poincaré return map. And well, the flow is smooth, everything is nice, but as soon as you induce this Poincaré return map and the section has boundaries, then the map has discontinuities. Why? Because sometimes you are very close to the boundary of the image. So if you move a little bit to one direction, then you will miss this piece of the boundary, you will actually hit another piece of the boundary. So the boundary of this disk causes a set of discontinuities here. And this is quite bad for us for the following reason. So the idea of Sarik to do that thing, and also our idea, is to try to implement passing theory. And when you implement passing theory, you need charts. And you have to control the sizes of the charts because, for instance, imagine that you want to apply graph transform methods. So you want to have some sizes of graphs for which the image of these graphs will cross entirely the domain of the next point. So if you have a point whose trajectory gets very close to the boundary, unavoidably, even though this point has a very good hyperbolicity, the chart you have to put here will have to be very small. So this boundary effect causes you a price that you have to pay, which is at some places where you are very close to the boundary, you have to diminish the size of these passing charts. So problem, the effect of the boundary, which can be solved as soon as you know that most points do not approach the boundary exponentially fast. So solution, if you prove that when you measure the distance of the iterates of a point to the boundary of the section, and they do not approach the boundary exponentially fast, so if this happens here for almost every point, then we are in a good situation. Because in some sense, this is telling you that the effect of the boundary is sub-exponential, and the effect of hyperbolicity is exponential asymptotically. So the asymptotic hyperbolicity will be stronger than the sub-exponential approximation to the boundary. And how do we do this? Well, this is the point where we actually need to fix a section for each measure. Because the idea is to do the following. Okay, assume that the section that we constructed does not satisfy this property, but you can change its size a little bit. So you can actually consider a one-parameter family of sections by changing the radii of these small disks. And well, if a trajectory approaches exponentially fast a fixed boundary, it will not approach exponentially fast other boundaries as you change the radii. I mean, the space of parameters in which you have this will be exponentially small. So in the end, with this one parameter family of sections, we are able to show that actually for almost choices of sizes of these radii, you are able to have this property. And then the proof goes. Okay? And actually, that's the reason that our proof also works for a countable family of measures. Because since you have for each fixed measure a space of parameters of full Lebesgue measure in which you have this property, you can just intersect these countable sets and then get a single section for which this holds for all the countably many measures that you have. Okay. So what I did with Jeroen Lamb and Sylvain Crozier was actually to bypass these boundary effects. So we are actually able now, Crozier, and myself, BCI, to prove that if you have a three-dimensional flow, for simplicity, it's infinity, no fixed points, and if you fix a chi bigger than 0, then you can find, as in Sarik's original work, a subset of the manifold with a countable Markov partition such that the measure of this set is 1 for every measure mu, which is chi hyperbolic. Ten minutes, right, Chair? 20? Ah, yeah, I started 4:40. Good. Okay. Okay, so it's about this that I wanted to mention a few words about the proof. So how do we bypass this problem of the section? So the idea is actually to consider two sections. So we construct one section lambda and another one lambda hat which contains it. So lambda will be the kind of the reference section. And lambda hat will be a security section. In the following way, in a way that when you want to construct passing charts, you will consider points in the smaller sections, and you will wait until it hits the smaller section again. And when you have the situation, since lambda hat strictly contains lambda, there is no problem of defining the passing chart here, whose domain might possibly go beyond the section lambda, but it will be inside the security section lambda hat. All right? So this is a piece of lambda, this is a piece of lambda hat. So the idea is to construct a set, countable set of such passing charts. So whenever you have a point here from lambda that falls into lambda, you are actually, whenever you have a point here which exhibits some non-uniform hyperbolicity, you can construct a passing chart here. And the good thing is that now on its image, you're going to be able to consider the full transition from here to here, because the image of the passing chart at the image point will be still inside the security region. So whenever you have so then you can approximate real trajectories by pseudo-orbits. This is actually not true. I mean, the idea is that in order to construct a countable object, the idea is to construct countably many of these passing charts in which the space of pseudo-orbits that you generate by it will be coding all of these points which exhibit some sort of non-uniform hyperbolicity bigger than chi. So this is more or less the idea. But what is the problem with that? So this means that construct countably many passing charts whose pseudo-orbits or whose space of pseudo-orbits shadows all relevant trajectories. And by this I mean points of M with hyperbolicity or non-uniform hyperbolicity at least chi. Well, let us assume that we have one such pseudo-orbit, which geometrically means that you have here, starting at x0, you have a point in the smaller section, and then you flow it until it hits the smaller section again. And next to f of x0, you have a point x1, which you go again until you hit the smaller section again, to f of x1. And then you have a nearby point x2. And the idea is that when you look at the passing chart at x0, the passing chart at x1, the passing chart at x2, whose domains might go beyond the smaller section, you have some sort of hyperbolicity in the transitions from here to here, from here to here. So you can define graph transforms, and you can shadow, using this sequence of transitions, you can construct an invariant manifold here, a stable, and the intersection is going to be kind of the unique point that is shadowed by the sequence of pseudo-orbits. But as soon as you have this point that's shadowed, there is no reason for it to actually belong to the smaller section. So I'm trying to draw it like this. So what could happen if you have a point which is very close to the boundary of the smaller section? This point here can actually belong only to the security section. Might not belong to lambda. And this is unavoidable. And even worse, you could have a real trajectory that is shadowed by different pseudo-orbits in various manners. So you could have a real trajectory that can be obtained as the intersection of these stable and unstable curves by a sequence of pseudo-orbits that are defined in very different times. So you could have a pseudo-orbit here with time t0, t1, t2, t3, and so on, and here t0 prime, t1 prime, t2 prime, and so on. In a way that it would be very hard to compare what would be the data of this pseudo-orbit, more specifically the data of the passing chart with the data of the other one. And if you are not able to do this comparison, then you are in trouble. Well, why? Because one thing that we have to have in mind is that only having the countable Markov partition is not enough. We also want this countable Markov partition to induce a coding that does not increase the complexity of the original system. So in some sense, we want that the suspension space, which will be, and I'm calling sigma R, induces a coding which is essentially finite to 1. Where every point here of the set NUH sharp should have finite to many preimages here. Why is this good? Because whenever you have a measure here, you can average it on the preimages. It's finite, it has no entropy, so the lifted measure will have the same entropy. So measures of maximum entropy here will come to measures of maximum entropy here, and this is good for us. So this all translates to trying to understand what are the different ways of shadowing a semi-real trajectory. And because of this problem here, that there is actually no real geometric meaning for the shadowed point, it is not even inside lambda, it's very difficult to compare one possible cutting, one possible pseudo-orbit of the real orbit with another one. Okay? So this introduces to us a new problem, which we call the parsing problem, how to compare different pseudo-orbits of the same guy, of the same orbit. So each pseudo-orbit, each passing chart, they are associated to a data. And in this business of non-uniform hyperbolicity, let me call a passing chart psi x. X is the center of the chart. Usually you have to define a size for this passing chart. So I'm going to put here a p. And Sarig introduced also a great thing, which is the following. Working only with passing charts, at least for what he aimed to do, is not enough. Basically because as soon as you define a size for the passing charts, you are in some sense saying that you are comparing unstable manifolds and stable manifolds morally of the same size. And it might happen that the center of the chart has a very different forward and backwards behavior. So in order to separate the behavior forward and backwards, what he actually considered is what he called double passing charts. So double passing charts are actually two passing charts centered at the same point, but with different parameters. PS is the parameter that you are going to consider almost horizontal curves, stable curves. PU is the parameter that you're going to consider unstable curves. So the idea is to apply stable graph transforms for things of size PS and unstable graph transforms for things of size PU. So the passing chart comes with a data, which means the point, and the point has stable directions and unstable directions, so it has invariant directions. It also has rates of contraction and expansion in these directions. And as I just said, it also comes with these two parameters, PS and PU. And the definition of a transition between two passing charts, so you allow one passing chart to follow another passing chart. Well, you need the point X, its image, to be close to Y, so f of X close to Y. You need Y, f minus 1 of Y, to be close to X. This is usually the definition of pseudo-orbit. But you also need all of this data here to be one related to the other. So the stable direction at f of X has to be close to the stable direction at Y, the unstable as well, and the same thing for the pre-image here. But you also need a relation between the parameters that allows you to apply graph transform methods. And the way that Tariq did was by requiring that, for instance, QU, what is QU? QU should be the size in the unstable direction after the iteration of the map F. So you expect that the map F will increase in the unstable direction, at least one amount. So you expect that it will be at least, QU will be at least of the size e to some small constant times PU. And the size has to be smaller than the global size of the passing chart, which I'm calling Q of Y. So QU has to be smaller than or equal to these two things, and the way that Sari required a transition to occur between two double passing charts is that QU relates to PU in this way here. It's a kind of a greedy way of getting the amount of expansion that you should consider at the image here. And the same thing for PS. So PS is the minimum of e to the epsilon QS Q of X. Okay? And by requiring the relation between these parameters of these charts in a way to satisfy this greedy recursion, he was actually able to prove that the coding generated by the countable Markov partition is finite to 1. This is a very delicate part of the proof. So, how much time do I have? Still 7 minutes, okay. So how do we do? Well, in our situation, you have a point here, X, in the smaller section, whose image, f of X, in the smaller section, is very close to the center of the next chart. So you should ask what happens for a transition here. And well, of course, you should require that the image of X is very close to Y. The pre-image of Y is very close to X. You should require that the invariant directions of these respective points are close. But what would be the relation between PS, PU, QS, and QU? In some sense, it also has to reflect the amount of time that you fly from here to here. Right? So what we do is the following. You have the passing chart here, the passing chart here. So first of all, we will not have no longer a nice equality like this. But this will be morally true. So basically, PS will be essentially of this size. How? It will be smaller than or equal to what we had there. But actually, we also have, as I said, you have to take into account the time it takes for you to go from X to Y. So you should put a time t here to take that into account. And this time here is the minimal time from a neighborhood of X to go to a neighborhood of f of X, and vice versa for Y. So you also look at the times that points in the domain of the passing chart at Y take to come back to a neighborhood of f minus 1 of Y here. So it's a kind of minimal possible transition time between the image of this passing chart here to the image of this passing chart here. And actually, it's not only that. I mean, we also need a lower bound, which is actually much uglier than only requiring this. So we need also this is less than or equal to the e to the minus epsilon ps times a minimum of the same thing here times q of y. And not only that, we also have to put an e to the minus epsilon here. So how did this definition came up? Well, we tried many things. None of them worked until we understood what could be done. So we had to diminish here in order to have an approximate equality, but also our methods didn't allow us to put here just q of y, so we really required this e to the minus epsilon. Actually, this should be q of x. And the same thing for q of u. So this has to be smaller than or equal to this, greater than or equal to e to the minus q of u, minimum of e to the t, u of u, e to the minus epsilon, q of y. And the problem that we had to deal was also in some sense that since you have a time here, you could have a time shear between two different pseudo-orbits. So the pseudo-orbits, one of them could be accumulating time in comparison to the other. And why this doesn't happen? This doesn't happen because in some sense we can apply ideas of hyperbolic times by considering certain parameters in which this guy is almost maximal. So you expect that things will grow at least of this rate. If they don't grow at least of this rate, it means that they are essentially maximal. So we locate points, positions, in which these parameters are essentially maximal, kind of hyperbolic times, PS essentially maximal, here and here. And we show that in between these essentially maximal times, the shear that you accumulate here, no matter how many pseudo-orbits you have in between, is bounded. So by having this bounded thing, you can actually compare with another pseudo-trajectory. This is almost maximal, you compare, so this is greater than or equal to the parameters here, but because you have a finite accumulated shear, this thing can be spread over to any position in the other pseudo-orbit. So by doing that, we are actually able to recover the main property, which is that the holding space that we construct is a finite one extension of our original flow. And so I think that I will stop here, so thank you very much.
Questions, comments?
The eigenvalues can be very small, right? Some of the eigenvalues.
Close to chi.
Yes.
So are they bounded by chi, or can they be lower as well?
No, it cannot be low. It has to be chi, bigger than chi or equal to chi.
Which means the times that the return times are bounded, like you said.
Yeah, the return times, I mean, since we construct a global section, the return times are always bounded. But the problem would be the accumulation of these return times in comparison to the real trajectory and the pseudo orbit. There could be a time shear between those two objects.
Said that we need a finite to one for the equivalence quality of entropies. But if it's countable to one, then entropies are already equal.
Yeah, that's true.
So why did you need finite?
Because, I mean, how do you lift a measure if it's countable to one? To lift the measure, then you should divide by the number of pre-images. Yeah.
Remember it's three-dimensional flows, but did you hope to, you need new ideas to go higher? Or
No, I need new good students to go higher.
Right.
That's what I think.
It's not just having to glue together the high dimensional maps and
Well,
that's definitely the big. Yeah.
No, now that we also know how the theory of Sarig works in higher dimension, partly due to Snib and Ovadia, I think it would be technically challenging to do these things for higher dimension. And maybe on the way, new ideas need to be developed, but I cannot foresee them now.
In this three-dimensional context, if the flow is infinity, entropy is produced, then you have measure maximal entropy. How far is it to obtain a unique measure of maximum?
We are working on that. So we believe that if you have transitive, well, this is being recorded, so I'm afraid of putting conjectures. So, but we hope that for transitive C-infinity flows with positive speed, there will be a unique measure of maximal entropy. Yeah.
And is it challenging because of having singularities?
For these things? Yes. I mean, the reason is that we don't know how to do it yet, but we expect to do it by constructing things on the section. So we have the idea of quadrilaterals, which are small pieces of stable and unstable manifolds. But we also need to deal with Young's theory. So we need to contract the tail entropy. And to do that, well, we have to be more careful.
Okay, so let's thank you once more.
Thank you.
So the last speaker, the session is Jeroen Lamb, who talks about horseshoe for random dynamics.
Okay. Okay. After a long day, I'm going to make an end to this, and I think Ian is already very happy that we need it at the end. Yeah, first of all, Ian, happy birthday. We've known each other for at least 25 years consciously, and I met you probably 30 years ago, first time. And because this is recorded, I can't really I can't really say too much, so I just leave it with happy birthday. Yeah. Okay, good. Good. Horseshoes for random dynamical systems. This is a report on some work that I did with Giuseppe Tenaglia, who's sitting here in the middle of the audience, and with a nice collared shirt, so it's hard to miss him. And with Dima Torayev from Imperial. And there's a preprint. Yeah, good. So what I'm going to talk about is about random dynamical systems. And I give some motivation first of the type of problem I'm interested in. And then I'm going to discuss some results that link positive Lyapunov exponents existence and random topological horseshoes. Good. So random dynamical systems are basically systems which are non-autonomous, driven by some process, and we have some probabilistic information about this process. So usually we assume some ergodicity, base dynamics, and we either have a flow like an SDE, some simple example like here, or we have some step-skewed superproduct, for instance, random dynamical system. So I think random dynamical system is very interesting, and also really a field that deserves more attention, not in the least because many people in applications seem to be convinced that whatever they're looking at has something to do with some noise, and that they like low-dimensional systems with maybe with more realistic aspects than kind of very low-dimensional deterministic systems provide. Now, just from a general philosophy point of view, of course, as I said, random systems are kind of a special case of non-autonomous systems. They're driven by something, but they're of course considerably easier because in some sense we can try to use the statistical properties on the base dynamics to get better ideas of the dynamics. So in general, non-autonomous systems are kind of more problematic, but we'll try to, in the random setting, to kind of use in some sense some aspects of these very measures in the base to get some results which basically hopefully holds for, say, almost all noise realizations or something like that. So it's an easier version of another very important problem, just generally non-autonomous dynamics. Okay, so here's an example of a mapping, and here's an equation. This is logistic mapping with some additive noise. So what I do is just iterate the logistic map, and I choose the parameter value of the deterministic mapping precisely in this period 3 window. So here's the parameter value. So I have normally have a stable periodic orbit, period 3. Almost every initial condition gets subtracted by this period 3 cycle. Of course, we have lots of other stuff going on in the background. And if you add some noise to this, what we see is that if you here's the parameter of the noise amplitude, and here's the phase space, basically the interval. So you see it, you get basically more and more observations. So at some point, you stay in a very small region. At some point, you break out, and then you get a measure which basically sits on the whole interval, and things can behave. And the question, like, what can you say about such simple random dynamical systems? And this specific example has been studied by many people, especially in the physics literature, also in the early in the 1980s. But so recently we did some other work here. Some people. Okay. So what we here see is we have lambda, is the Lyapunov exponent. So what you see here is there's some position of this behavior. So on this epsilon d, we have basically the measure breaks out of these 3 intervals around the period 3 orbit. It breaks out because it's bounded noise. So we increase the amplitude of the noise, and then we have this Lyapunov exponent, and at some point it crosses through 0 and then goes up. So the idea is somehow that we have some position here to chaotic dynamics, in the sense that the Lyapunov exponent becomes positive for a large enough noise amplitude. And the question is, can this be understood in some sense, why this happens and how this happens, and what does it mean for the dynamics? Because of course, this Lyapunov exponent is just basically some statistical average over derivatives, and it doesn't necessarily say so much what's going on with the underlying dynamics. So in colloquial terms, this is like, go from order to chaos, but in some sense, the question, like, what does that then precisely mean? Good, here's another example, just to kind of emphasize the importance of the dynamical properties. So here's an SDE. It's a very special form. This is some kind of like Hopf bifurcation form. Has rotational symmetry, which just adds some kind of Brownian motion. And then you can actually kind of study this. So usually people would study the dynamics in some sense looking at the stationary measure. So in this kind of example, you can actually calculate stationary measure by hand. And so the kind of equation is some exponent of some minus potential. And so what's interesting here is that basically there's some parameters here, especially parameter B, which is a shear parameter, which doesn't arrive at all in the stationary density. K is just a normalization constant. Good. So if you look at the probabilistic properties of dynamics, it doesn't depend on B. So here's an example. So the deterministic picture would be either an attracting equilibrium point or an attracting limit cycle, and then you look at the stationary measures and you see things that look more or less similar. We see kind of like some distribution here. Stationary measures, it's around the stable equilibrium or the limit cycle. Yeah, so no surprises here. But now if you look at the dynamics, there's actually quite a difference. So we can look at so-called pullback dynamics. So that may be a bit technical, but just think of take a number of initial conditions, just run them forward and see what happens to them. And so in some for some parameter values of B, low parameter values, what happens is that all the initial conditions under the same drive with noise go to actually 1 point. So we call that sometimes noise-reducing synchronization. But if B is large, then what we see is that the limiting object is very different. Of course, this is a non-autonomous setting, so if we keep looking at this picture, this point is going to move, it's a moving target. And this is a more complicated picture. So how do we, there's a lot of results about this kind of synchronization feature, and this is associated, for instance, by negative Lyapunov exponent and some mild other conditions that we have this. So you see that, basically the future dynamics doesn't depend asymptotically on the initial conditions, or we have some sensitivity to initial conditions if we have some kind of chaos with positive Lyapunov exponent. But the question is, like, what is this dynamics precisely like? So what can we say about this chaotic dynamics? Good. So this shear-induced chaos example has some history. For instance, Lysa Young and Kevin Lin looked at this, and also Sebastian Wieczorek at the same time, and then he did a number of studies, tried to understand if we can actually prove at least the bifurcation in terms of Lyapunov exponents, and this can be done. Here's a number of papers, first computer-assisted some stuff, and there's some recent paper by Maximilian Engel and Dennis Chemnitz. Good. So what I'd like to talk about now is basically kind of topological consequence of positive Lyapunov exponents. And as was Yuri just mentioning, this result as well. So if we, there's an old result by Katov, basically saying that if you have a positive Lyapunov exponent and some which doesn't suggest formation on periodic orbit, then we have actually transversal homophilic. So it's quite important. It means that in some sense, having a positive Lyapunov exponent does tell you something about the underlying dynamics. As, not about everything, but at least some aspect of it. So we know that chaotic dynamics means something like shift dynamics. So here, you can positive Lyapunov exponent implies topological horseshoe. And you'd like to have something similar, probably for the random context. Good. So just to sketch the setting. So if we have negative Lyapunov exponents, then we often have synchronization in this sense, that the limit of time to infinity of two initial conditions will actually kind of converge to the same trajectory. One should actually kind of keep in mind that this could be, this looks kind of really neat, but in practice, usually it's very complicated because this convergence may not be uniform. So it may depend strongly on the noise realization. So you get actually very complicated transients, and they can be very long and non-uniform. And so there's lots of issues with that. Which actually may also be important in understanding the transition to positive Lyapunov exponents, because even for negative Lyapunov exponents, you see a lot of features that we see. For instance, this kind of pictures you also see with negative Lyapunov exponents for a very long time sometimes, and then only in the end, basically this kind of picture kind of shrinks to a point. So there's transients also associated to these things. Good. So, question, general question. How does noise-induced transition to chaos in random dynamic systems arise? Yeah, that's, I think, an interesting question, because of course in the deterministic setting, it was also a question that received quite a lot of attention, like roots to chaos and stuff like that. And so the question, how does it happen in random dynamical systems? So some observations, simple examples, especially by Ali and Holmberg, is that often we have some kind of like at the point of zero Lyapunov exponent, we have intermittent behavior. And also recently he found kind of an infinite invariant measure for two-point motion also at this transition point. So if we get we basically get the enormous sticking points to kind of like 2 points coming very close to each other, a measure that sits on the diagonal. So the measure goes to infinity near the diagonal. So it's not clear to what extent this is a general phenomenon or whether this is peculiar for some examples and so on. Good. So you can ask, like, how to understand this. I'm also working with another PhD student, Bernard Bassols-Cornudella, about like approximating dynamics. Basically, in these examples, you have some kind of like competition between contracting dynamics and expanding dynamics. You can try to kind of like measure this. So you can try to kind of build some kind of approximation by finite state Markov chains, for instance, using so-called condition processes. Anyway, but that doesn't really reveal much about the underlying dynamics. It just basically tries to kind of tell the probabilistic story in a slightly different way. But the question that I'd like to kind of address head on here is what kind of random dynamics is positive Lyapunov exponent? Is there an analog to Cattock's result in the random setting? So in dynamical systems, of course, there's a whole issue about probabilistic results in deterministic systems, but you can of course also turn around. You can ask, like, are there topological results on probabilistic dynamics? Good. So I think that we try to kind of achieve such insights on like what's going on beyond the probabilistic observations in systems. Good. So here's a simple example. Just to fix ideas. So this is slightly different. This looks a bit like this logistic map, but it's essentially different in the sense that we can say something about this example and I can't really say much about the logistic map. So here's a simple example. This is some kind of science map with large L and additive noise. And this is a deterministic picture. And there's a lot of things going on. If L is 3.25, you precisely have a periodic orbit. You have two fixed points actually, with zero derivative, so it's kind of super attracting. So we get some kind of window here, and again we have also complicated things in the background, and we see similar pictures before. If I increase the amplitude of the noise, then what we see is that the Lyapunov goes from negative to 0 and then to positive. I also here's a plot of basically some impression of the density. So you see, of course, if this noise amplitude goes up, then this density becomes more and more uniform in some sense. So you can also guess, like, at least for sigma lax, you roughly the Lyapunov average of the derivative. So you can also see in this example, if L is large enough, you should probably get positive Lyapunov. But the question is basically what happens in such an example. And one of the questions is, like, if you have positive Lyapunov, do we get horseshoes? Should we expect some kind of horseshoe dynamics in this kind of example? Okay, so here's a result that applies to the specific example. So there's a bound here, sigma is 0.42. That's well off the scale here, kind of here somewhere. But it doesn't make it less interesting in my view. But it's just we should kind of keep note of this. So we are far away basically from this bifurcation point, but at least from for big enough noise, the following result, if sigma is large enough for this fixed value of L, then the random sine circle map that we just have has a positive Lyapunov exponent and the random horseshoe, in the sense that there's full measure set in terms of the noise of noise realizations, such that it's some kind of expanding constant kappa. So for every pair of connected disjoint intervals I0, so I take two intervals I0, I1, and then what I get, I basically get a sequence of return times that has good average. So it has like it is a random time, but it is a good average, such that we get shift dynamics. So we get basically some kind of dynamics which you end up in. You get two intervals you can map in any sequence between I0 and I1. You have expansion on these things, and you have basically this kind of partitioning of these intervals. So you get basically a usual shift dynamic for every pair of initial intervals I0 and I1. So it's very chaotic. There's an abundance of horseshoes. Everything basically makes horseshoes. Of course, you can also play this game with more intervals and do whatever you want. So it's very, very clear. Good. So the idea is here that somehow this is a kind of result which is quite strong, but also, of course, we assume a lot of noise, but it's not obvious. So importantly, the underlying system we took here is not uniformly hyperbolic. So we have basically contracting and repelling behavior at the same time. So we need to kind of play a game here where we try to understand how these things happen. Okay, so there have been some similar results in the literature by Zheng Yan and Wen Wang, where they assume basically a kind of like uniform hyperbolicity in fibers. So this is a bit different game because you have already uniform behavior, and then you look at what the noise does. So they don't have to overcome attractivity. There's also some result here by Wen Wang and Kenning Lu talking about weak horseshoes. About the technical issues that actually these weak horseshoes essentially only really say something about finite time horizon behavior, so they really don't really take time to infinity, really. So it's not unlike ours. Okay, so how can you obtain this kind of result that we just advertised? Is to look basically, try to kind of understand things probabilistic ways using hyperbolic times and some kind of like estimates on light deviation. We want to basically know how how orbits behave and how often they come back in some kind of probabilistic way. So papers that we've used particularly is Baladi, Benedict's, and Mom Deschamps, and also Joseph's book. So what's the technical challenge? If you look at Katok's book, then of course kind of it looks basically at return times, and if you have a deterministic system, as soon as you find a good return time, then basically return time is constant. So in some sense, actually, he finds superior points also by the fact that you have constant return time. But if you in the random context, you typically have no periodic orbits because you don't have constant return time. So you need to kind of work your way around it. So in the beginning, we try to somehow find drastically some kind of like periodic point somewhere, but that doesn't seem to go anywhere. So periodic orbits are related to constant return time. In the random setting, we hope to get good behavior of return time so that they basically have good average, or so that we have some kind of good control over how often points come back and then do something with them. And then hyperbolicity is controlled by using hyperbolic times adapted to this random setting, and also some kind of ideas of how the Lyapunov exponents behave. So finite time level exponents for time go to infinity, how they converge to Lyapunov exponents. You need to control over these things. And that's basically what we do. Okay, so the main hypothesis of this work is basically work with piecewise C2 circle maps, positive Lyapunov exponent, sufficiently fast decay of the tail of the new distribution of the finite time Lyapunov exponents. You must make sure that somehow you see almost Lyapunov exponents at some point with some controls. And you also want some existence of a uniformly expanding interval that is ultimately mapped to the entire circle. So in some sense, this example that we have, there are some kind of like full branch properties in there. And there's a positive probability for any given interval to be eventually mapped to the entire circle. Yeah, so we try in some sense to make sure that small intervals do grow, and that at some point they map to the whole circle. And that's in good territory, because once we are the whole circle, we stay on the whole circle, and we can use that. Okay, so the strategy to prove is that very small intervals eventually grow uniformly with good control on times, and small intervals are eventually mapped to the entire circle. So basically very small to small, and then small to the entire circle, again with good control. And then the latter phenomenon produces an abundance of topological horseshoes, because at some point when we find mapping to the whole circle, we're done. So just to go back to this logistic map, then this latter part doesn't work. So we have some problem if you have too much noise in the logistic map, if something will escape to minus infinity. There's nothing we can do, and we don't really get such good control there. And so we can't really use this kind of last step. If you can map to the whole circle. So the circle is really definitely easier than this logistic map. Good. So what I want to do is just kind of flag here the kind of technical assumptions that basically go through things in more detail. See, so we have a step-through product, so we assume that the noise just depends on some kind of sequence of symbols, of which we just basically take always the first symbol. And then we must make sure that somehow these mappings G omega, so these are the mappings for given no serialization, they are continuous, they have a finite set of non-differentiability points. We have uniformly bounded first and second derivatives in this set, in the C2 norm. So we make sure that somehow things are not too bad. Of course, this is a standard assumption that, of course, these things are measurable. And we have some kind of singular set, but we both can take the points where we don't have derivatives and zero derivatives, and these are points that we like to avoid. It's the usual game in non-uniform dynamics. We try to kind of stay away from these things. So here's some kind of technical type of condition that is quite standard to look at. You want to kind of basically this set of singularities to be regular in the sense that we have some kind of constant, so we can kind of basically say something about how these distances of points to the set compare to derivatives and so on. So these are kind of things that are typically being done. Yeah, so we need to kind of some regularity in the set, so we can't just have any example. It must be sufficiently nice. But for instance, in the example that I gave, we just have a finite number of zero derivative points, critical points, and no points of non-differentiability, so it's relatively tame. Good, and of course we need the Lyapunov exponent, so we assume that we have unique stationary measure equivalent to Lebesgue, and then we have Lyapunov exponent given by this under this usual equilibrium condition. Good. Now we need to have some probabilistic estimate. So what we're going to do is we have some kind of assumptions that will kind of lead to the result that we have horseshoes, but that doesn't give me any result that actually is happened for a given example. So then we have to kind of find some kind of like sufficient conditions so that our hypothesis is satisfied. But here's a algebraic decay of the probability of the Lyapunov of the sum here. The finite Lyapunov exponent is basically having certain bounds. So we look at finite sum. This is smaller than some kind of lambda n, and then this probability has algebraic decay. Good. Now, there's two types of things we want to control. We want to control basically how the Lyapunov exponents behave, but also how we approach critical points. So the game is basically we have expanding dynamics, we have contracting dynamics. Contracting dynamics happen near the critical points, so we need to stay away basically from critical points. So we need to kind of some estimates of that. So here's some kind of like estimates of distance from the critical set. But we want basically some kind of slow recurrence of points to the critical set. So look at some quantities like this. You want to basically control those things, and by efficacy you can basically kind of like equate this also with this integrals here. So we want to for every epsilon we want some delta such that this kind of condition is satisfied. So we have slow recurrence to the critical set. Good. Yeah, sure. Hypothesis 1, yeah. 2, 1. This is just usual. Here we say that basically. Yeah. But later we have to come, of course, show that this example, for instance, has this property, right?
And then we will use that structure.
Yeah, so these estimates may be a little bit absurd. They're not absurd, but they're strong in the sense that if we have all these conditions, then somehow we can get the result we want. The question is like now, can you show that this happens for some class of examples? Good. Yeah, so we have here some kind of control behavior of fine time exponents. Good. So here's the control of visiting neighborhood with critical point, and then we have another estimate that the probability of this being larger than a certain kind of thing is now kind of controlled again by some kind of algebraic decay. Yeah, so they're kind of technical things, but it's not my comfort zone. I can admit somehow, but other people clearly know, and Giuseppe definitely knows very well. Good. So we have this kind of these assumptions, and then we assume now that small intervals actually eventually map to a full circle with positive probability. So taking some kind of interval, then for some omega, some noise realization, and some kappa 0 is in the kind of measure of expansion, so that I is an omega kappa 0 capital K full branch expanding this interval if there's just a subinterval I and some integer bounded by K, such that the I filter for this kind of omega realization is actually the whole circle, and that you also have expansion. So you basically ask, like, you know, this is an interval or something. It's an interval that after I, at least no more than K iterates, basically goes to the full circle in an expanding way. Good. So this definition, and the assumption was the following. The assumption is that there exists some kappa 0 such that for all sufficiently small eta greater than 0, exists a natural number K and some iota in 0, 1, such that for every interval with some kind of bound on this interval, on the size of this interval, we have positive probability that I is actually the full branch expanding interval. Yep. So we have positive probability here that so it's important here that this K, of course, depends on the sizes we take, right? So if you have very small sizes, then the K will grow. Good. So what do we get out of this? Yeah. Well, there's some balance between noise and so we can take L very large and noise not so large, or we take noise very large and L also large. Yeah. That's right. Good. And another thing we need the dynamical system to be such that it's almost surely full branch expanding on some random subinterval. So for P almost all omega, there exists some interval I omega such that after one mapping, this interval actually maps to the full circle. Okay, so sometimes it's 5 implies 8. Okay, so we have 0 to H0 to H5, and this gives you quite a thing. So now here's the definition of a random horseshoe. So we say that I0, I1, two intervals, so disconnected, and that omega be initialization and kappa be expanding constant. And the pair is called an omega K horseshoe that exists a sequence of return times, such that it has a mean, P almost surely, and also a family of subsets here forming the horseshoe in such a way that basically when we map the first return map of these intervals, you can map from ij to j, from I to j under the fixed times, and you have also kind of like expansion factor. So we basically have the usual kind of horseshoe. Since we call this an omega K horseshoe for fixed omega and fixed K. Good, so theorem. So if our random system satisfies H0 to H5, then exists a full P measure set omega tilde. So almost surely this is true, and some uniform constant kappa, so that every joint pair of intervals is a omega kappa horseshoe for all omega in this full measure set. Yeah, so the idea is to kind of basically prove this, and then to show that somehow that the example fits into this somehow. Okay, so what's the ideas here? You need some kind of control on return times. So but we need some kind of stopping time, and so we need to kind of control the probability of stopping time being larger than some L, and we want this to algebraically decay. So if this is the time stopping time is saturated for some realization of the noise I has a subinterval J that maps to the full circle, then we want to make sure that somehow this is doesn't grow too much. As L goes larger. And so how do you obtain this? Well, this is basically two steps. One is basically using Lyapunov exponents to make sure that things do kind of like grow. So small, very small intervals grow to larger intervals. And then we want to, using H4, we want to make sure that basically we have this kind of positive probability of the interval to be full branch expanding. And if we have that, then what we do is we exploit the independence of the product measure, and so find that basically this intersection of these kind of events for k larger equals 0 it goes to 0, and then as a result we have an almost sure bounded time and some kind of interval that takes the kind of maps to the entire circle. So we have a bounded time to the first step, and then we have kind of capital K basically to map to the entire circle. And then this also has a good bounce on the hyperbolicity, because we get some kappa here, which basically is balanced between the kappa 0 we had here and the kappa 1 that we got before. So we get an almost sure bounce on the stopping time with some kind of hyperbolistic estimate. Good. So now we have with H5, which was the fact that we have this kind of an interval that's mapped to the entire circle. We get the property that we have to almost sure an exception for any two given intervals I0, I1 of a sequence of social return times there, and then we basically kind of take we just basically see how both map to the whole circle, but because when you map to the whole circle, you stay on the circle, you just take the maximum of both, and then you get basically expanding and overlap both intervals, and we can basically construct a horseshoe in this way. So it's important, of course, that we have some kind of like good averages of this difference between these return times, and which is given given by this observation that these times are independent and identically distributed. Okay, so now we can do that for basically all intervals, and so take intersections of those sets, all full measure sets, so we can kind of get some full measure set of noise realization for which this all happens in some uniform way. Okay. So questions like, to what kind of example does this apply? So there's a kind of class of examples that we describe here called predominantly expanding random circle maps. And we take basically some kind of like conditions now that should assure that we have H1 to H5 or H0 to H5 satisfied. So first of all, we want the singular set to be nice and not too bad. And so the first second derivative of G is bounded away from 0. In this, so we have a mapping here, which is basically kind of additive noise. It's written slightly differently than in my example, but of course it's just a matter of whether you put the noise first and then the deterministic map, or first the deterministic noise, but it doesn't really make so much of a difference. Good, and here's another assumption, is that we look at so-called super expanding region. So we take some R, and we don't look at this is singular set, it should be as. Then what we want to make sure is that if this set of where we have this kind of lower bound on the derivative, that this is the connected components of these the size is larger than 1 over R. So what does it, how does it help? It helps that we see that these regions are mapped in one iterate to the whole circle, basically. So if they are large enough, and we have the kind of growth rate R, then we map immediately to the circle. And then there's some other assumptions. The noise should be large, and here's another technical assumption. This should be there, so there's some relation between conditions here on predominant expansion, also by Young and recently Blumenthal. So the statement now is that the sigma R predominantly expanding random circle map satisfies hypothesis H0 to H5. And means that every pair of the joint intervals is almost sure omega k horseshoe. So the earlier mentioned example of the signed circle map with L is larger than 3, so it's 3.25. Then this is true with some kind of conditions here, and if you calculate these values, you get sigma is larger than 0.42. So the intuition here is that condition 2 here gives you this property that the noise amplitude is large enough to escape the set in one iterate, and the other condition is basically interpretable as some kind of estimate for the Japan exponent. So consequence of this condition is, which is useful, is that there exists some h so that sigma is larger than dr, which is some constant that was defined before, divided by 2h, and it turns out that this equation here implies that this total frequency is strictly to this set of contracting points, something that don't expand by r is actually smaller than h. So you can basically h is some kind of like upper bound for this total frequency to visit to the complement of the super expanding region. So you want to kind of get a lot to the super expanding region. Anyway, okay, so this is going to prove. Some parts are easy and sometimes some are less easy. So 0, 1, 5, and 4 basically follow in some sense from the conditions. And for H2 and H3, one has to look a bit more carefully about its estimates. It's all rather technical, but I'm sure if you're interested, you can look it up, preprint. Okay, good. So we get some kind of conditions that for which is true, it's clearly maybe not what we really want, but okay, one has to count the blessings that you have, right? So this, I think the assumptions are rather extreme, but still we establish there's a bunch of random horseshoes, and the question is like, can you kind of like push that to regions which are closely to bifurcation points, for instance, and understand better to what extent such things also hold in general when you have the Japan response positive. So the idea is really to try to get a characterization of the dynamics in random dynamical systems, and ultimately I would say some understanding of what precisely this bifurcation from negative to positive Japan response does to the underlying dynamics. So as I said before, the result we have here does not apply at all to the logistic map, and that's something that Giuseppe is looking at the moment. Another thing which I think is important, that controlling topological properties of dynamics, also random dynamical systems, may be useful to obtain good probabilistic results. So also in deterministic systems, of course, there's often quite a mix of arguments that are being used, not just probabilistic arguments, but also topological underlying arguments to just kind of help the argument forward. So I think actually spending some time trying to understand topological properties of random systems is not a waste of one's time. Good. Well, we all want some wine or beer or something else. I just want to be a good citizen and advertise some results of PhD students. So Giuseppe recently produced a paper with Matheus, who's also sitting here in the center. Basically, kind of have a result on quantity correlations. With similar kind of attitudes, we have some kind of random dynamical system with some kind of nice properties. So it's not too many critical points and good behavior of the derivatives and so on and so on. You look at this kind of example, and again for a large L limit, they obtain basically exponential quantity decay correlations with an L goes to infinity, and they basically use similar kind of idea. So the important thing is again that it's non-uniformly hyperbolic. It's not, but of course there is a kind of a large L. Anyway, so here's a result, and I was told that there will be a poster of them hanging up somewhere from tomorrow. So if anyone's interested, please have a go. So this is all for me. Thanks very much, and let's have some drinks and stuff like that.
Any questions, comments?
Yeah.
Jeroen, can you put that page 12? I have a question about
page 12.
The circle map. Yeah. So if you look at a region where the Lyapunov exponent is still negative,
Suppose I start with zero noise and tune up the noise.
Yeah.
Okay, zero noise, the distribution will be 2 delta functions.
Mm-hmm.
And as I tune up the noise, this will become, I guess, Gaussian or whatever. Right?
Well, there will be some transition here when first it's because it's bounded noise, things stay first bounded somewhere they will break out in some non-discontinuous way.
What I'm wondering is there a signature when it covers the entire interval? Before that, is there a signature? I mean, do those distributions change somehow?
Well, you can actually calculate for those examples precisely when your intermeasure starts covering the whole circle.
But what about the distribution? About those 2 delta functions. Those delta functions become distributions.
Well, that's kind of complicated. We had a PhD student who worked basically on such a transition. So when the thing break out and look at the asymptotics of distributions, that's not Gaussians here, clearly, because it's not a. But there's characteristic behavior of the distributions near boundaries, for instance. So there's some marked differences of asymptotics. Yeah, but it's not Gaussian because the problem doesn't lean itself or Gaussian in some sense. So, but it's not a Gaussians are made for certain kind of problems, not for this problem. Yeah, but yeah.
This was more question about the end.
Yeah.
So you talked about random long-tails. Your main theorem, your main abstract theorem with these hypotheses, especially H2 and H3, look like Alves, Zato, and Pinheiro in a deterministic case, and they build deterministic long-tails. So why aren't you getting a random long-tail right from the beginning?
It's not my favorite.
The big question, yes. So
yeah,
but the H2 to H3 was your paper. Yeah. So in that paper, you're basically building a young tail over the horseshoe. So why aren't you, apart from the controlling the return times, because you required only 1 over into the quarter, and over into the 4. But the theory of Alves, Zato, and Pinheiro says if you can build a young tail and you've got decay rate for that return time, then you can prove decay correlations and some other limit laws. So why don't you have that already? That was my question.
Yeah, I didn't think
about the problem, but why don't we have this already? Why don't you guys
get it for free?
First result doesn't make power because you have a partition. We have just started the return to theorem 1, but you're not making a partition. Roughly speaking, what
But part of the application that's a Pinheiro is you use those assumptions to build partitions. Part of the theory of application that's a Pinheiro is you use those hypotheses to build.
There is some theory in the determination case of construct power for some one-dimensional type of system with a positive level of exponent and other properties. In particular, some uniform transitivity concept that would be deployed. And the problem in the random case is that the transitivity is a uniform component. So what happens in a theoretic case? The reaction of exponent, roughly speaking, the hyperbolic times, you have a transition from a very, very small scale intervals to a visible scale, which happens very often. And then you have a transition from a visible scale to a reference set, which is where we make power. The problem in this transition is uniform. That are just transitivity in this way. In random case, it's not possible. And what you lose the fact that when you wait, if you wait too much, going from the visible scale to the reference set, you lose, for example, uniform distortion estimate. The more you wait, the more the distortion constant grows. So if you can wait infinite many times, you don't have distortion estimate. And the real problem among these guys is actually how can you overcome this difficulty? And let me explain this way. The first paper gives more or less the tools to construct the result for decay correlation in a random case, which I would say is actually what I would say more proud of that I have done. Makes sense. To know what's possible about it and more.
So in the case of the Mandelbrot model, if you induce always on the right hand side, you just have a horseshoe with a variable return times. If they want horseshoes with the same return time. If I understood your question.
Yeah, but what he's saying is well, like roughly speaking, what they're saying in the horseshoe, what you're doing is that philosophically speaking, you are taking a power reference at the circle and you are taking just a subset, the return time that we cover again. But of course, from this on how to create a procedure that allows to extract from a cover a partition that's going to return for reference, that is another word solution. So it's a bit more different. I hope you answered.
Questions? You expect to have a theory as kind of a second step, which approximates in entropy.
I didn't. Of course, you'd like to have also kind of notions of entropy that work well, and that And you would like, of course, a more richer expression of what kind of the dynamics is. So one type is it's kind of underlying deterministic or topological behavior, and another one would be we haven't looked at it yet, but that's clear.
So, a question: if you change the kind of noise, not uniform noise, these are use truncated Gaussian. How
shouldn't be. You want to make sure that I think it's not too sensitive to precisely which kind of noise, as long as you have something which is diffusive. So yeah, you one point was the distribution of the back measure, you get the back densities. Of course, some of these things will change a little bit somehow, and estimates will change. But I think basically it's not we're not really doing a probabilistic calculus somehow, which really is essential. So as long as you have measures that can behave well, then of course we use the properties, but it shouldn't be crucial. You don't do stochastic calculus here. Somehow. So we should also be able to relax some of these things. Of course, we take here very simple setting in some sense. It's as simple as possible to not break all our bones somehow. But it should be possible. Once you get the results, you probably extend it and look at all kinds of other settings where similar results before.
So I know you are all eager for more discussions. Let's continue tomorrow. That's next week.